Up until now, we've really been doing really mostly image processing, where you take an image in, some I of x, y, and you apply some function to it, and you get out a new image, what I'm labeling here as I prime of x, y. And that's great, and there's whole courses, in fact, entire careers, hundreds of thousands of PhDs written on image processing, but that's not why we're here. We're here to talk about real computer vision. In real vision, you still take an image in, but what you get out is good stuff. All right, the whole idea is that we're putting images in and we're getting stuff out. So what are some examples of stuff? Well, maybe just a line. So here we have an image on the left and some edge description of it in the middle, and you can see a whole bunch of lines that have been found within this image. Or maybe you want to find circles. Actually, it's a little hard to see, but there's a bowling ball there, and the way the bowling ball was found was find all the circles in the image. Well, guess what? There's only one circle, and that's the bowling ball. Or here's some more circles. Just find the coins. And in fact, I'll tell you that this particular picture was put together by a TA of mine a huge number of years ago. He's now a pretty famous researcher doing stuff on I can't say where. But this was in order to show how to do a Hough transform on circles. And you might even find good stuff as like, find me this car. So you see on the left here just some examples of where we might locate the car, but actually the car is found right in the middle. Actually, this is a notion of an arbitrary shape. In fact, we're going to get to how to do finding an arbitrary shape. Actually, not this lecture, not this lesson, not the one after it, but the one after that, where we talk about a generalized Hough transform. Today we're going to focus on finding parametric models. And what we mean by a parametric model is that it's a class. It's a model that represents a set of instances where each instance can be represented by a particular setting of the parameter or the parameters. So for example, a line is a parametric model, a circle is a parametric model, and like I said, we'll even be able to talk about a parameterized template, where you have a template, but you change its shape according to the value of some parameters. So when you're trying to fit a parametric model, or another way of saying it is you're trying to find a parametric model inside your image, there are essentially a couple of things you have to keep in mind. The first is, what parametric model are you going to use? That is, how are you going to represent, how do you go from the parameters to the thing you're representing? And in fact, today we're going to show you that even for something as simple as a line, how you do your parameterization matters. The other thing about this model, and this actually works to our advantage, is that the membership, or the notion that a little point in the image or an edge or a template belongs to a model, is not determined by just looking at that edge. You actually have to look at many different edges or look at the whole model. And that notion of extended support is something we're going to take advantage of. And then finally, whenever you go looking for a parametric model, you could just say, well, if computers were infinitely fast, and every time we use one, they feel like they're becoming infinitely fast, well, I would just check for every possible line in all possible places. Well, the reality is that even with really fast computers, the number of possible models is really big. So it turns out you're I'm losing track here. It turns out you're a really fast computer. Still, you have to worry about the combinatorics of your computation. Here's a simple example, okay? Line fitting. And you might wonder, why might I want to find lines? Well, as the example shows here on the left, you might want to know that your chips are seated correctly, so you see the lines on the chips. Or this is the tower, again, from University of Texas, and you find the edges, and you might just want to see whether or not you might be in the state legislature, and you want to make sure the tower at the University of Texas is not leaning to the left. That's a joke for some of you. But we're going to assume for now that finding lines is something we want to do. So you might be wondering, well, wait a minute. We just spent a long time learning about how to find edges. Aren't we done? Can't we just find the edges? Well, if that were true, I wouldn't be standing here. So let's talk about the difficulty of line finding. So here's that same University of Texas tower, again, courtesy of Kristen Grumman, and we've run an edge operator. And what I've done here is I've pulled up a part of it just so we can talk about some of the phenomena. So problem number one is that there's lots of points here that have nothing to do with the lines. Okay? So all these little edge points down here, these have nothing to do with the lines, so we have to be able to deal with them efficiently and rapidly. Second, only parts of the lines are actually detected. So for example, here you can see that there's this big gap in the line, even though what we'd really like to do is say that we found the entire line. And finally, there's noise and corruption actually where we do find the edge. So over here you'll notice that in these lines across here, there's all this stuff that doesn't exactly lie on the line. You can see the pixels are jumping around here as well. So we have to be able to go from these noisy measurements of where the edges are in order to find the actual lines.
All right, let's try to build some intuition about how to go from edges to lines. Remember that edge images are just collections of pixels. Pixels like these where possible lines could be found. How many lines can you identify in this image? So you could identify lines in different ways. For instance, this could be a short segment, a longer segment to the right-hand side, and a diagonal cutting across. Now this is a consistent set of line segments, which almost accounts for all of the edge points. But there are other possibilities. For instance, this long segment going right through, and two shorter segments on either side. There's no single correct answer to this question. If you entered 2, 3, or 4, we would accept it as correct. Hopefully this will give you an idea how finding line segments in an image is not a trivial task. This is especially true if you don't have any additional context and are looking at edge pixels individually.
As I said before, it's not feasible to check every possible line, even with a really, really fast computer. What we have to do instead is somehow allow the data to speak to us, allow the data to decide where the lines are. And because this is democracy, what are we going to do? Well, we're going to do something called voting. So voting is a general technique where we let the features vote for all the models that are compatible with it. And the way it works is pretty straightforward. We cycle through all the features. Now, today, for mostly features, what I'm going to mean is little edge points, all right? And each edge point is going to cast a vote for the model parameters or the different sets of model parameters that it's happy with or consistent with. And when we're all done, we look for the model parameters that receive a lot of votes. And those are the parameter models that we're going to instantiate. Why does voting work? Well, voting works for the same reason that Mickey Mouse, Donald Duck, and Lara Croft are never elected governor of California. Angelina Jolie, maybe, but not Lara Croft. You see, what happens is, in every election, there are people. There could be millions of people who are unhappy with the main candidates, the real candidates, if you will, and they'll write in some silly name, Mickey Mouse or Lara Croft. But even if there are millions of silly votes, as long as they don't all put down the same silly name, then in some sense a real candidate will get elected. And this will work unless Stephen Colbert or somebody like that tries to orchestrate an overthrow. But in general, the idea is that these silly votes are all distributed across sort of the not important candidate. So this works the same way for our computer vision. Noise and clutter features will cast votes too, just like the real features, but typically their votes should be inconsistent with the majority of the good features. Also, another nice thing is, even if part of the circle, say, is occluded and there are no features there to vote for it, because the rest of the circle has gotten a lot of votes, we're able to find the circle. So the example we're going to use today to start with is just on fitting lines. All right? And to fit lines, we're going to have to ask a couple of questions. First of all, given points that belong to a line, what is the line? That is, you know, which line are they picking? How many lines are there? And which points belong to which lines? Now, we're mostly going to focus on the first question for this lecture, and in fact, most of what we'll do, but extensions to what we're talking about make it easy to do questions 2 and 3 as well. So the method that we're going to talk about today is called the Huff transform. And it's a voting technique that can be used to answer all these questions. And the main idea is just that voting principle. Each edge point is going to vote for compatible lines. That is, it's going to vote for any line that would go through it. And then you look for the lines that get many votes. So there might be 2, 3, 4 lines, and you can find all of them. And by the way, if you keep track of which points voted for which lines, you're also able to go back and say which points belong to that line. So I'm going to take you through sort of how this works. And the key to the Huff transform is Huff space. here we have a line in image space, and you all remember the very first equation you saw of a line somewhere in Mrs. Thompson's or Mrs. McGillicuddy's or whoever your Mrs. Mine was Mr. Zebro, actually. He was also the football coach. I learned algebra from the football coach in junior high school, which is a very strange thing. Anyway, so you remember that the equation of line is y equals m0x plus b0. So what we're going to construct is what's called Hough space, and it's really the Hough parameter space. And in lines, in this representation, we have two parameters, m and b. So for this line, y equals m0x plus b0, that's represented at a location in the Hough space at m0, b0. So there it is. There's the point in Hough space. A key idea here is that the line in the image corresponds to a point in Hough space. Okay, you got that? A line in the image corresponds to a point in Hough space. Now we're going to do something a little different. Suppose we only have one point in the image space, and we'll put that point here at x0, y0. Well, what are the equations of the lines that might go through that point? Well, in image space, we know that the line that goes through that point is going to satisfy, for whatever the m and the b are, it's going to satisfy the equation y0 has to equal m x0 plus b. Right? That in order for it to go through the point x0, y0, it has to have an m and b such that this equation holds. Well, with some very simple algebraic rearrangement, that becomes b is equal to minus x0m plus y0. That's the equation of a line in MB space. In fact, it's a line with slope negative x0 and intercept y0. Okay, so the idea here is that a point in image space is a line in Hough space. This is the duality. Well, if we have one point, what happens if we have a second point, x1, y1? Well, that's going to be another line, right? That's going to be a line with b equals minus x1m plus y1. And so now here's the really cool question. What line would be consistent with both points? Well, it has to be the point where these two lines in Hough space intersect, because that's the m and b that's consistent with being on a line that goes through x0, y0, and on a line that goes through m1, b1. And this, ladies and gentlemen, boys and girls, and all you interested parties, this is how we're going to find lines from points. So now we have to reduce this to an algorithm. We'll first do it graphically and then actually show the algorithm. So basically, every point gives me a line in Hough space. So what I do is I create a grid. Here it's of m and b. We're going to change that in a minute, which are made up of a set of bins. And every point votes for a line's worth of bins. So it casts a vote in every bin that it goes through. You collect up all the votes, and after every point has voted, and whichever bin has the most votes, that's your line. So this basically, we're going to be casting votes into bins and then finding the bins that have sort of a large number of votes, larger than sort of the average noisy area. Before we implement this in real code and real math, we're going to have to rethink our representation of lines just a bit. You might remember that there were some issues with the MB representation of lines. In particular, for example, a vertical line is really painful, right? Because m is equal to infinity, and in 7th or 8th grade or 9th grade or 12th grade algebra, the notion of having an infinite slope is kind of very painful. All right? So what we want to do is we want to use a more robust representation of lines so that we don't have any sort of bad numerical problems. So what we're going to use is a polar representation for lines. So in our polar representation, this purplish line here is going to be defined by two quantities. One of them is just this distance d. This is the distance of the line to the origin, the perpendicular distance. It's the distance to the closest point on the line to the origin. And the second parameter, so that first parameter is d, and the second parameter is theta, which is just the angle that this perpendicular makes with the x-axis, or if you want, you can have it be the angle that the line makes with the axis. Doesn't matter. You just have to pick an angle. So basically what we have now is a polar representation of an angle and a distance. In such a representation, by doing just a little bit of math, you can basically see that the dot product of any point on the line xy, dotted with the cosine theta, sine theta location of this normal is equal to d. There's a lot of ways to do it, but basically you can show that if you formulate it this way, that x cosine theta plus y sine theta equals d. So it's a lot, not a lot, it's a little bit ugly. Well, it's beautiful if you like trigonometry. It's ugly if you like algebra. It's a little bit more ugly than the y equals mx plus b formulation, but it doesn't have this problem that any of our lines are ill-defined. This is a perfectly fine way of representing any line. You can have any direction you want. Theta can go however it wants to go, and you can go right through the origin. D can be 0, or it can get as big as you need it to go. One of the interesting things now is, if you take a look at this equation, if I know x and y, what I have left in terms of d and theta is a sinusoid, all right? Which is why we say that a point in image space is now a sinusoid in Hough space, and we'll see an example of that in a minute. See, before we had this beautiful duality of a point in image space was a line in Hough space, and a point in Hough space was a line in image space. Well, because we've introduced this cosines and sines, it's still a duality, but it's no longer just simply between points and lines. One other comment about this. There's a redundancy or an ambiguity here. Let me draw it to you this way. Here's d. So if d can only be positive, this line has to be able to spin all the way around. So theta would have to go from 0 to 2 pi, 0 to 360 degrees. But if d could be positive or negative, then theta only has to go from 0 to pi, or 0 to minus pi, depending on how you draw that. The idea is you'd only need 180 degrees worth of coverage. Which way you do it doesn't really matter. In our algorithm, we'll do it in a particular way. But there's just this trade-off between if you let d go positive to negative, positive and negative, then it only has to go 0 to pi. In fact, you can restrict things even more. If you make this be the origin of your image, the top left-hand corner, if you're going to say that your line has to be within the image, okay, then that restricts even more because it has to cut off that quadrant, so theta and d are restricted even more. But these are just choices that you make in terms of how you code up the algorithm. So speaking of the algorithm, let's take a look at it. So we're going to use the polar parameterization of the line, the polar representation, and something called a Hough accumulator array, which is just a fancy word for the thing that's going to collect the votes. You're basically going to have an array, 2 dimensions in this case, where the bins represent different values of d and different values of theta. One of the things you'll have to decide, and by the way, you'll be implementing this, is how big are the bins? How many of them are there? So if it goes from 0 to, let's say, 0 to pi, well, if you have every 1 degree, then there'd be 180 bins. If you had every 10 degree, there'd only be 18. So you have to decide how big the bins are. So given this equation in the accumulator array, here is the algorithm. And I hope you appreciated that I tried to color code this. It looks garishly ugly, but it tries to keep everything clean. So the basic Hough algorithm is this. You initialize your accumulator array to 0 everywhere. Then for every edge point, so we have to have a set of edge points. That is, at every place in xy, we have to know whether it's an edge point, or we have a list of them. Somehow, we know which points are edges. In fact, how do we know that? Because we did that last time, right? So you know how to do this in MATLAB or Octave, or you can write it in assembly code if you're really masochistic. So for each edge point xy, what we do is, so here I use theta from 0 to 180. That's, supposed to be 1 degree increments. All right. Solve for d. We just use that equation. Since we have x and y and we have theta, we can solve for d. But notice I'm not doing anything to restrict d being positive or negative here. So it could be positive, could be negative. And I have to then set h of d, comma theta. I have to increment its vote. So if d is negative, what I really mean is the bin of that d. So maybe my d goes from minus 100 to 100. So I would have 201 bins if I do them by steps of 1. So if I got a minus 20, I'd have to add 100, that'd be 80. You get what I'm saying, right? The d value goes into its bin. So the bin of that d value gets incremented by 1. After you've done all the voting, you find the values of d and theta where h of d of theta is a maximum. So you want to find these peaks. By the way, in MATLAB, there's a function called Hough peaks, which, by the way, you're not going to be allowed to use because you're going to have to write your own peak finder. All right? Well, anyway, let's assume you found just one d and theta. Well, the line itself would be d is equal to x cosine theta minus y sine theta. Get it? That's all there is to finding these lines given the edge points. So we did an algorithm. Whenever you do an algorithm, you just need to think about things like how well does it work? Well, obviously it works great because I'm telling you about it. No, we'll see that in a minute. More importantly, for algorithms, we have to talk about things like complexity. So the first question is, this is the easy one, what's the space complexity? That is, how much memory do I have to use? Well, forgetting the image for a moment, the bottom line is I need k to the n bins, all right? So if I have k bins in each dimension, it's k to the n is the number of bins. So we were doing this in 2 dimensions, so it would be k squared. So, if I have about 100, so it's about 10,000 maybe. That should tell you, and this is going to come up in our next lesson, that adding the number of parameters, which increases n in this case, can be very expensive in terms of memory. In fact, also in your problem set, you're going to try to do something and you're going to blow up MATLAB, and then you're going to figure out how to fix it. What about time complexity in terms of the voting? Well, the nice thing is that the voting is linearly proportional to the number of edge points. You run through your edge points and they each vote. And the voting might take a little bit of time, but it's constant, all right? Compare that, let's suppose you're trying to fit a circle, okay? So a circle is defined by 3 points. So if you have some large number of edge points, the number of triples is that number, let's call it q. Q choose 3 would be a very big number, right? Whereas if you do something that's proportional to just q, you're in much better shape. So the idea here is that the time complexity is constant in the number of features or edge points that you've detected. Let's take a look at some examples, some toy examples and then some real examples. Here we have a cartoon example of an image on the left that just has a bunch of dots in it. And those dots happen to all lie on a line, which is good. So this is a noise-free Huff example, of which there are none in the real universe, but I've got one here. No, I was about to say I made one. No, I stole this one. Others I made, these I stole. So on the left here, in image space, we have a bunch of points that all lie on a line. And they lie on a perfect line, so that's how you know this is a cartoon example, because that never actually happens for real. What we have on the right are the votes. And what you can see here is that each dot is creating a particular trace, and you'll notice that those are parts of sinusoids. Okay, here's another one. And that comes from that equation that I was saying before. And what's most important is all the votes over here line up, and that's how we would know that's where the line is. See? So cool. All right, suppose I showed you the picture of a square, all right, and I ran an edge detector on it. What would you expect to see in Huff space? Well, let's see. How many lines do we have on a square? That you learned hopefully before 7th grade. There would be 4 lines, okay, and you would get a Huff accumulator array, a voting thing that looks like this. And here you see that there are 4 peaks. It's a little hard to see sometime in the image, but the idea is that the values there are much higher than the values elsewhere, and you can see how the votes overlap. So here you would know that there were 4 lines, and you'd be able to pull them out. Okay. Here's another Blocks World scene. You can see that there's a bunch of edges there, and here's the Huff array, and you can see there's sort of sinusoids dancing all over the place. Here, by the way, you see one really big bright spot. What's that spot going to be? Well, that's going to correspond to this nice, big, long edge. There are other spots, and that makes sense because there are other lines. But this big, bright one is going to be the longest one because it has the most votes. We'll take a minute here to do a little demonstration of using a Huff transform that's built into MATLAB. And I'll repeat, on your problem set, you're going to be doing some Huff code, and you're not to use the Huff implementation that's already there, nor anybody else's Huff implementation that you have from the web, because it turns out when you go and write your Huff implementation, certain things are going to break, and it's in that experience of it breaking that you're going to learn what the important elements of it are.
To detect lines in an image, we first need to find edge pixels. So let's load an image, convert it to grayscale, and find edge pixels using the canny operator. Let's see what these look like. Here's the original image. As you can see, it has some lines in it, the grayscale version, and edge pixels. Now we'll apply the Huff transform method to find lines. For this, we'll use the Huff function in MATLAB. Find out more about this function in the MATLAB documentation. The equivalent function in Octave is HuffTF. The first return value is the accumulator array. The second is a vector of theta values, or angles, and third is a vector of radius values, or rho. Let's see what this looks like. We pass in the theta and rho values to properly label each axis. Rho, or distance from origin, is along the y-axis, and the angle theta is on the x-axis, ranging from -90 to +90. Okay, so let's find the peaks in this accumulator array. We pass in 100 as the maximum number of peaks we are interested in. Note that a similar function called immaximas needs to be used in octave. Let's plot these peaks on the Huff accumulator array. Note that we need to use the theta and rho values to plot the peaks correctly. The peaks are marked by small red boxes. The size of the peaks matrix is 13 by 2. 13 peaks were found. Each row contains the location of a peak. The first column has rho values or y values, and the second one has x values. Using these peaks, we can find line segments using the Huff lines function in MATLAB. It looks like 28 line segments were found. Each element in line segs is a structure with the two endpoints, the theta and the rho values. Let's plot these line segments. As you can see, most of the longer line segments have been detected, but a lot of spurious line segments also show up. Okay, so how can we get better results? Let's take a look at the edge pixels again. We notice that there are breaks along the longer lines in some areas. There is also this dense grouping of curves that could throw the Huff detector off. To find a set of cleaner or more meaningful lines, we can do multiple things. For instance, we could increase the threshold parameter for Huff peaks. To understand what these parameters mean, let's look at the documentation for this function. So threshold is the minimum value in the accumulator array, that is the minimum number of pixels that support a line required for that line to be counted as a valid candidate. Any possible lines with less pixels will not be considered. Here we set it to be 0.6 times the maximum value in the accumulator array, the default being 0.5 times max. Neighborhood size defines the region over which local maxima will be computed. Note that this is not a region in the image. We are computing local maxima in the accumulator array. So the size of the neighborhood is defined in rho and theta dimensions. A neighborhood size of 5 degrees along the theta dimension means that a strong line will suppress other lines that are similar but slightly off in direction. Recall that we found 13 peaks in our last attempt. This time we have only 7 peaks. Let's see where these peaks are. Looks like we might have cleaner results after all. Let's compare this with the previous accumulator peaks. We see that a lot of the previously found peaks in this dense region are now gone. The new peaks are clustered around 3 major locations. Okay, what more can we do? We could play with the parameters of Huff lines. How about we increase the fill gap parameter to 50? This is the maximum number of pixels allowed between two segments for them to be counted as one if they lie along the same line. To focus on longer lines, let's increase the minimum length to be 100 pixels. For a better understanding of these parameters, take a look at the documentation for Huff lines. Okay, let's see what the new segments look like. Compared with the previous results, we see that the false positives have been mostly removed. Some of the previously broken segments have also been joined. Obviously, you can do a better job by playing with the parameters, especially here. So feel free to play with the Huff transform functions.
Here I'll show you an example of Huff running on a real image to show you that what it does well and what it doesn't do well. This is a picture of an American football field. This is American football, played with a ball that's not round. We run an edge detector of some flavor and we get out these edges, and those are some interesting looking edges. And then what we do is we run that through a Huff accumulator array. You can see the sinusoids here sort of spread out, but you're seeing that these squares are all of these peaks that were found. And this is using some code that tries to look for peaks. And you'll notice that a whole bunch of them are very close together, right? So being very close together would mean that they're about the same angle and that they're approximately in the same location. Same angle, same location. Well, yes. I mean, here are lines that are the same angle and about the same location, and here, and here, and here. And even here, about the same angle, about the same location. So you would expect to find peaks that are nearby. So I'm showing you this peak image here. If I were to draw the lines associated with each one of these peaks, I would see something that looks like this. So there's good news and bad news on here. The good news is that it found an awful lot of line segments. Okay? You'll notice it also missed a bunch. Okay? Why is that? Well, that has something to do with the nature of the edges that were found and the bins and the voting. These are all details that are going to matter in terms of how well you find the edges. You'll also notice that there is this cyan line here, and that's the longest line segment found. Now, somebody should be saying, wait a minute, line segments? What do you mean by line segments?
Line segments? What do you mean by line segments?
Well, in the Huff transform, when you find a theta and d, or an m and b for that matter, that's an infinite line, right? That's a line that goes as far as you want to. It certainly goes through the entire image. If you want to find the line segments of the points that voted for that line and just connect them, or just connect the two that are farthermost away, or do some other operation of running along that infinite line, seeing if there's an edge point near there or anywhere near there. So you have to do some other operation besides the voting we just showed in order to find the line segments. The good news for you is that in your problem set, I just want you to find the infinite line. You don't have to worry about finding the line segment that's actually supported in the image. A couple little things to look at remaining. The first is the impact of noise on the Huff transform. So here what you can see is an image on the left where we've taken that same cartoon set of dots and we've perturbed them a little bit off the line. So we've added a little bit of noise to their location. On the right, you see the Huff votes. And you'll notice that now the peak, not so precise. And in fact, if we had very, very fine bins, we might miss that peak altogether. So in a minute, we're going to talk a little bit about changing bin sizes with respect to noise as a way of making the thing work. But what happens is that small amounts of noise can bump you off. So by the way, one really kind of cool thing you could do, if you wanted to find sort of the general peak over here, what might you do? You might smooth this image, right? You could actually take say a filtering of that as an image. Then find the peaks, and now you know you've moved the peaks around a little bit because you've blurred it, but now you at least found the peak, and you can say, I'm going to do the Huff transform again, but this time I'm going to just focus on that area. Okay, so I'm going to build a new array with much finer bins, but only there, and if D or theta are outside there, I'm not even going to count those votes, and that would let you go from a noisy image to a better one. There's actually another problem. What happens if we have a lot of noise? Like, suppose all we have is noise. Here on the left, what you've got is a bunch of points that are put down that are just randomly put there. And on the right, everybody gets to vote. Laura Croft or whoever you want, go ahead and vote. Turns out there were no real candidates. But maybe we don't know that. You can accidentally find peaks. So sometimes you have to worry about, is the peak that I'm finding actually real or not? It's helpful if you already know. Let's suppose you know there's 6 lines in the picture. Well, then you just find the 6 highest peaks. But if you don't know how many are there, you have this question of when is a peak a real peak and when is it just the accidental alignment of votes? To conclude this lesson, I want to talk about a couple of extensions to the Huff transform. And then some of these extensions are going to carry over both to the next lesson and the one after. By far, sort of the extension that people leverage the most is the one shown here using the gradient. You'll notice that our algorithm is almost exactly the same. We initialize our accumulator array, we iterate over each point, but now instead of looping or iterating over all possible orientations, we actually take the gradient at that point and we take theta from that gradient. Now, you could take a single theta, or you might even take a range of thetas where you say, well, I know that it's approximately 45 degrees plus or minus 10, so I'll vote from minus 35 to 55, but I don't have to worry about voting for all the others. I've written it here as if you got a single value. Now that you have theta, you can solve your equation directly, just as we did before, and we increment our accumulator array. The nice thing is that by using the gradient, you've reduced the voting time hugely, right? You don't have to worry, you just have a single point. Also later you can use it to reduce the dimensionality. So this is the extension that people make use of the most. In fact, the whole notion of orientation is something we'll talk about more going forward. A few other extensions. One is, well, remember when we were doing edge detection, we said that some edges had stronger magnitude than others, and you have to set a threshold. Well, you might lower that threshold a bit to try to get more edges, but the idea is you might want to count the edges with a higher threshold more. Well, what would it mean to count them more? Well, you can imagine that stronger edges would get more votes. Another extension, and this is similar to what I was talking about before, is playing with or changing the bin size of theta and d. As we said before, big bins make it easy to, first of all, vote, it's fast, but you sometimes can get similar lines landing in the same bin. Too fine a bin, and you have this problem that the real line, because of noise, votes for different bins. So extension is to do this hierarchically. First, do a coarse binning where you have sort of larger bins that capture more values. Once you find peaks there, you then go to finer arrays just within those areas, and you improve your recovering of the model. And finally, it's not just an extension, but it's a whole new way of doing things. We did this for lines, but you can do this easily. I shouldn't say easily. You can do this pretty straightforwardly for other parameterized types of shapes, like circles, which in fact we will be doing in a little bit. Oh, and you'll be doing as well. Or actually any other shape, including shapes that are defined by their templates. So that's the end of this lesson. You will undoubtedly go back and look at this pretty carefully, since this algorithm and the manipulation of the data sets are going to serve as the basis of the first part of the Huff problem set. And when you look up this stuff on the web, which many of you will, you'll want to relate that back to what was seen here. And I'll tell you this, implementing the Huff transform feels relatively straightforward. That's why people, when it was on a course where the problem set was due Sunday night at 11:55 p.m., many of them started it around 6 p.m. They later reported that it took them more like 10 hours to do this problem set, and that's because the extensions, the circle, etc., nothing quite works exactly like I say it does. That, by the way, is going to be a lesson of this class. The papers, first, what we say in class never works, because it's a distillation of the simple stuff. What we say in papers hardly ever works, because we have to make it very, sound great for publication. In reality, stuff works. You take the theory, and then you have to massage both the imagery and the algorithms. All right, welcome back to computer vision. So having done lines, and remember lines are sort of the easiest version of a parametric model, now let's move to something just a little bit more complicated, namely circles. So here's the equation of a circle. You remember this from Mrs. McGillicuddy's algebra class. X minus a squared plus y minus b squared equals r squared, where a and b are the center and r is the radius. And for now, we're going to assume the radius is known. How did you know it? Megan sent you a postcard and said the radius is 11. Okay, fine, so you know the radius. Oh, and we're also not going to use any gradient information just yet. We're just going to find the location of the points. So here we have a circle. We don't actually know where the circle is, but we've detected, say, 3 points on that circle, the blue dots here, okay? So what is the Huff space? What is the accumulator array space for the circle? Well, since there are typically 3 unknowns, a, b, and r, but I told you we know the radius, Huff space is just a and b, right? The center locations in the x and y direction. So now let's consider the first point. So let's say x0, y0, this point right here, okay? So that point has to lie on the circle, and we know its radius. So one way of thinking about that is that the circle has got to be some radius r around that point, all right? And so what that does is it votes for a set of points. And that's what this green line represents, right? This set of points that are around this location in the AB space, okay? So for a single point in the image space, we get a circle of radius r in the Huff space, all right? Let's move to the next point. Well, same thing, right? So it's got to be, again, a radius r around here, and in Huff space, we're going to vote along this circle. And again, the next point. And so if each point votes, each point in the image votes for a circle, we collect all the votes. And so just as before, we get the majority of our votes here, and that corresponds to this middle point, and that's what's drawn there. So it acts just like before, where we're voting for lines, except now instead of using the sinusoids, we're voting in a circle in an AB Huff space. And in fact, here's a nice little example of the thing running. And this is taken from a very ancient photo, but you can see right in here, there's a bowling ball, and that's where the crosshairs are drawn. And just as a sort of to show you some other way of trying to find this ball that's moving, you can imagine just looking for the stuff that's moving. After all, it hasn't hit the pins yet. But when you look for the stuff that's moving, they find this bounding box. How come we find more than just the ball? Well, actually, if you take a look really carefully, you'll see that this lane is very shiny. Okay? In fact, in a little while, we're going to talk about reflectance functions and specular reflectance functions, and you'll talk about why on this lane you actually see the image of the ball, and because of that, there's motion in here as well, so you get this bounding box. But that's okay. What we're saying is basically that it was able to find the circle. Here's another example taken, in fact, if you go and you type Huff transform circles or something like that into Google and look for images, you'll come up with this image. This image was actually taken by Vivek Quatra back when he was a wee graduate student TAing my class back in 1811 or something like that. And what we did was we took a picture of these coins on top of a textured background. He did it because he had to, because he was my TA. He's now really a famous guy doing cool research stuff. All right? So basically, you can take this and you can compute the edges, and then here's an edge image of that, and then we can look for circles. Now, we're going to use the known radius method. So let's suppose we start with the radius for a penny, all right? And you can probably see that there's this nice bright spot right here in the middle. That corresponds to the penny. Now, what you may also notice is that there are these kind of blown up areas, not so much here, it's a little harder to see. We'll go back here. And that's because you could fit a penny sort of around the edge of this circle, and the centers would be rotating around the middle of the circle, and that's what this little circle of centers is. But at the real penny, they all line up, and so you get even a brighter spot. So how would we find the quarters? Well, we just use a bigger radius, the radius of a quarter, and we vote again, and again you'll see these spots here, here, and here. And now the penny edges, well, they again vote for this bit of a circle, but not nearly as strong as the quarters do. So this was the original image, and these are the combined detections. And so that's pretty cool, you can just find the circles. But suppose you don't know the radius, okay? Megan sent the postcard to the wrong place. You moved because you wanted to upscale your apartment, and now you know you shouldn't have because you're left without a radius. So what do we do? Well, let's think about it this way, all right? Now our Huff space has 3 dimensions, A, B, and R, because we don't know what the radius is, all right? So now if I have a single point, what happens? Well, now, if we knew the radius, let's say the radius was, 7 over here, then it would be some sort of a circle centered about this point, right? Just like that we did before. And if the radius was, let's say, 3, it would be another circle centered about the same point, but smaller. So I hope you can start to see that what we're getting in here is actually a cone, okay? So with unknown radius, each point votes for an entire cone in this 3D space. So the surface of the cone, right? Not a filled-in cone, but the cone that's a surface. And the next point, what does it do? It votes for another cone. And you can sum these all up. Now, I will tell you, this is pretty painful. And in fact, if any of you end up doing a problem set for some random course like this one, we're going to tell you in terms of looking for circles, if you try to vote in a great big 3D space, it's not going to work so well, and in a whole bunch of lectures later when we teach you about ransack, it'll sort of overcome this dimensionality. But for now, just know that we have this little problem of growing the size of the voting space. So it can be done, it's just a little bit painful. But remember before, one of the ways we got rid of the number of votes you had to do was by using the gradient direction, okay? So, because if I had a point and I knew the gradient, there was only one possible line it could be. Well, we can do the same thing with circles, all right? So now we have an unknown radius, but we have a gradient, All right. So again, our Huff space is A, B, and R, but this time our one point here has this gradient. Okay. Well, now if we knew the radius, we would just have one possible circle it could be, right? So if you tell me that this is a point and that this is the gradient and I know the radius, that's the only place the center can be. But if the radius was half that, then the center would be there. Or the center, I guess it also could be on the other side. So there's just this single line of voting that can happen when you have the gradient, and that's drawn like that. So in the Huff space, even though it's a three-dimensional Huff space, you would only vote along one line. Okay? And so that's a little bit better. At least it makes the voting easier. You still have this problem when you have this three-dimensional Huff space. So here's the algorithm sort of simply described for circles. Just like before, for every edge pixel, for each possible radius, right? So we don't know the radius. And then either for every possible edge gradient, if we vote for the cone, or if we use the estimated gradient, then we compute A and B and we increment for A, B, and R. All right? And then that would just vote you in your Huff space. In general, even though 3D is only 50% more D than 2D, you'll find that voting in 3D is way more than 50% harder than 2D. And that's because just one way of thinking about this is, let's suppose you had 100 buckets in each dimension, okay? So how many would that be if you had one dimension, Megan?
100?
And if you had two?
10,000.
And what if you had three? All right, that's 1,000,000, right? 10 to the 6th. The number of cells that you have to consider is exponential in the number of dimensions. And that's a challenge with using the Huff transform. So a couple of practical tips with voting for the Huff transform. One thing you want to do is try to not do too many irrelevant votes. So try to minimize sort of edge elements that are not robust or highly unlikely to be useful. Because remember, we don't have to find all the points along a line, just enough of the points. You want to choose a good grid discretization for your Huff accumulator array, right? How many bins you make. And there's no sort of magic answer to that. It's a little bit of an art. The problem is if things are too large, the bins are too large, then too many sort of false points vote for the same bin. And if the thing is too fine, then a little bit of noise will cause you to vote for the wrong bin. So there's this trade-off. It's sort of how coarse and fine the data structure is. There are other things you can do. You can actually say, well, I'm going to take my point and I'm going to vote for the bin, but maybe I'll also vote for bins nearby, because maybe I'm not exactly where I need to be. It's a little bit like smoothing in the accumulator array. That actually can help. Using the gradient or the edge direction reduces the degrees of freedom of your voting by 1, and sometimes that's very useful. And then the last thing is, once you found, let's say, the circle or the line, you could go and draw it in the image. But if you actually wanted to find the edge points, well, you could do a couple of things. One is you could actually try to look along that circle looking for those edge points, or you could have been more clever to begin with. You could have, when you voted in those buckets, in those bins, you could have kept track of every point that voted for that bucket. And then once you have a winning bucket, you go and you look in that bucket, and there's the list of points that voted for it. And that way you could find the points in the edge image that actually selected that object. So some pros and cons of the Huff transform. All the points are processed independently, so it's okay if part of my stuff is occluded because each point just gets to vote. There's a modest amount of robustness with respect to noise. So because the noise points, as we said before, they're unlikely to sort of collude to vote for the wrong thing. And you can use it to find multiple instances of the object within the single image. There are some downsides. The biggest challenge is that the complexity goes up exponentially with the number of model parameters. So you're never going to use this if you've got like 7 model parameters, or maybe even 4 that you're trying to explore. You'll have to use other methods. And the other thing is, if you have sort of non-target shapes, suppose instead of circles you actually had slightly squashed ellipses, then the voting can break down, and you have to be careful in terms of how you handle that. And as we said before, the quantization, it is hard to pick a good grid size and does require experimentation. Look, that ends the lesson on using Huff transform to find circles. That, along with the lines, is sort of very old approach to a parameterized method methods of finding parameterized objects. Even though it's old, it's a good way of learning about extracting structure from an image. Remember, we go from pixels to things. And that's actually why it's the first sort of serious problem set for those of you who are taking the online class or those of you who just want to try it. And by the way, it's also one of the first problem sets I give my on-campus class because they're not used to this idea of going from sort of an image to a data structure. Next time, we're going to talk about slightly more general uses of Hough transforms, where your parameter is not based upon an analytic model like lines and circles, but instead is based upon the shape of the object that somebody gave you. And we'll talk about how to do that and also why that has developed a little bit of a resurgence in recent years. So today, what we're going to do is we're going to finish up Hough with two significant changes. The first one is we're going to use non-analytic models. So it's not going to be lines, not going to be circles where our parameters were analytic parameters. Instead, the parameters are going to express, say, the orientation or the scale of some fixed but arbitrary template. The second thing, and this we'll only talk about briefly, is a visual code word based approach where we use what are called visual code words for the features instead of edges. And this is much more modern computer vision. Edges really came from an older view of how objects would be described. And now the focus tends to be a lot more on individual features. And later in the course, we'll talk about interest points and features about those points because I don't want to teach you just old computer vision. So that was the first one was then, and this is the now. For a generalized Hough transform, it was easy when we had a specific shape because based upon our equations for a single point in an image or a single feature or a single edge line, we would know how to vote. We would essentially solve for the equation that would tell us how to vote in the bins. But if you have an arbitrary shape, how do you know how to vote? Well, the way you do this is you build what's called a Hough table. It was actually called an R table in the original article, but I think of it as a Hough table. The way it works is as follows. For each boundary point, and here we have our first one, P1, what we do is we compute a displacement, or an R vector, from that point to, here I've got it as the center, but it's some reference point. This is the point that we're going to use to locate the object. All right? And we measure that R. That's a displacement vector. The next thing we do is we compute the gradient and edge orientation. And what we do is we take that R and we put it into a table that's indexed by theta. All right, so if we had some other point that had the same theta, it would also add its R to exactly the same table location. So you would have multiple displacements, and I'll show you an example of that in a minute. But the idea is that you create the R based upon the offset, and then you index it by theta. Here's our second point, P2. It has a different theta, and there would be a different R entered into that table. So we store the displacements in a table indexed by theta. At recognition, we essentially go backwards. What we do is, at every boundary point, we compute the theta that's there. By the way, for now, we're assuming that the orientation of the object doesn't change. In a minute, I'll show you how to solve it when, well, more than a minute. I'll show you how to solve this when the orientation does change. So at every boundary point, here's P1, we figure out the orientation. We go into our table, we find all of the displacement vectors that are associated with that orientation. So there's going to be this one. Maybe there were some others as well. But we're definitely going to vote with this one for this point. Then later at P2, we find its orientation. We find all the displacement vectors that are associated with that orientation. That one's definitely has this one, so that votes as well. And the whole idea is that the correct reference point gathers a whole bunch of votes. So what you're doing is you're using this table, this R table or Hough table, in order to tell each point in the new test image how to vote. This was originally done by Dana Ballard, and I point out that this is back in 1980. 30 plus some odd years ago. And that's just a way of showing you that what goes around sometimes comes around even in computer vision. So let me take you through an example now. And in this example, here you've got a picture, I'm going to assume a few things to make it easy. The first thing I'm going to assume is that we've got these little edge elements, these gradients, and I'm going to assume that we know which way is inside to the edge and which way is outside. It just makes it easier for the image for indexing. So let's start by looking at all of those bottom horizontal edges that are pointing inwards. All right? So they all have the same theta. All right? Now, as we go across all those different edge elements, they each have different displacements to the center. So all of those red lines, those are all the displacements associated with being a bottom horizontal edge. So if I found a little bottom horizontal edge, I'd have to vote with all of those displacements. So what that would look like at runtime is as follows. So here I have a little edge element, and it's voting for all these different displacements, which all would lie along that line. Where did all those different displacements come from? They're all here. These were the displacements for every possible bottom edge line, so every one of those vectors have to be voted by each bottom element. So that's just one element, but of course there's the next element. It has to vote the same way. It comes from the same theta, and another one, and another one, and another one, and eventually this big long line of possible offsets are voted for. Now, I didn't indicate here, the one in the middle is actually voted for more often, so maybe you can think of the middle as being thicker than the ends, but the idea is that this line has the votes for where the center might be. We don't know where along the center it is yet. Well, now what we can do is we can take a look at the downward pointing diagonals. And you'll notice that for the downward pointing diagonals, it can be anywhere from being straight above it all the way over to the right of it. Okay? So it can be straight above it or all the way over to the right. So what this means is at runtime, each little diagonal element has to vote straight above it all the way over to the right. And that's what's represented here for the first part. And here's another diagonal element, and another diagonal element, and another diagonal element, until finally they've all stacked up. And you'll notice already I know where the object is. This is how the center was found. So the idea is that we're using this table of those offsets indexed by the gradient in order to vote for the center. So the generalized Hough transform, or general Hough transform algorithm, is very easy. If the orientation is known, you know the orientation of the object, you do exactly what I showed you. For each edge point, you compute the gradient direction. You retrieve the displacement vectors R for that direction to vote for the reference point, and the peak in this space, in this case we're only voting in x, y, that's the reference point, that's where your object is. It's the one with the most sort of supporting edges. Now, it's sort of unreasonable that you might know the orientation and the scale, so let's talk about orientation. Okay, suppose the orientation is not known. Well, all we have to do is try the different possible orientations, and that's written here. Again, for each edge point, but now we have what we'll call a master orientation. This is the actual orientation of the object. For each orientation, possible master orientation, we compute the gradient direction, but we subtract off the master. So the master here is this theta star, the actual gradient is theta, but the gradient we're going to use is this theta prime, which is just the gradient with the overall orientation subtracted off of it. And so now we retrieve the displacement vectors for theta prime. So we're still voting, and peaks in this Hough space are the reference point, but notice now that we're voting in x and y and also theta star. So you remember that space complexity, which was k to the n? Well, n just went from being 2 to 3. And the bottom line is any decent sized number squared is much smaller than any decent sized number cubed. So you just got a lot bigger by going to this, adding this orientation. What's kind of cool, by the way, and this was in the original arbitrary shapes paper, you could also do this for, say, scale. Suppose the scale was unknown. Our algorithm looks stunningly similar for each edge point, but now instead of having a master theta, all right, we have a master scale. So for each possible master scale, we again compute the gradient direction. We again retrieve the displacement vectors, but now we have to vote with the scaled displacement vector scaled by s. And again, we vote. Whichever gets the most votes is the right point. And the peaks in this space, and now the space is x, y, and s, where s is the scale. So again, it's cubic. Now you can imagine that if you had scale and orientation, that would be quartic. That's raised to the fourth. Modest numbers raised to the fourth power are brutal. So you have to be careful in terms of how you do this. For the last part of the lesson, I want to talk about a much more modern approach to using these Hough transform displacement vectors. In fact, it was proposed as recently as 2004 and subsequently as a way of locating a particular object. What we're going to do now is, instead of using edges, or the idea of high value gradients as a feature that you can find, what we're going to use are little feature patches. All right? And feature patches are just little chunks of an image that, for some reason, for one reason or another, you've decided these are useful things to try to go find. So if you have those, this is the way that would work. So we have a training image here, and I'm going to assume for now that our feature patch is this tire, and I'll tell you in a minute about how we go about finding those feature patches. All right? And so here I've located the tire in two different places. And so in the same way as with the gradient, so when I first find it here, I say, okay, there's a displacement vector to the right like that, and I'll put that in a table that's indexed by the feature patch. And then I find it, I found it again, it's over here, and it's indexed, and it has a displacement vector to the left like that. So I put that in the same table, and in fact it's indexed by the same feature type. So these features are referred to as visual code words, which I'll describe in just a minute. And the idea is that I would have a table based upon the code words, and associated with each code word is the set of displacement vectors that I have to vote with every time I find that feature anywhere in the image. So the first step in training are developing what's called visual code words. And basically the way it works is this. You have some sort of an operator, and we'll talk about interest point operators, that generate what are called interest points. That is, these are points in the image where reasonable amounts of interesting stuff is happening, and we'll talk about Harris corners and other ways of finding that. What you do is you take your interest point operator, pull out all the interesting points on a bunch of training images. You collect a little image patch right around those points. You may get hundreds of them or thousands of them. And then you cluster them and use some algorithm for doing the clustering. And when you're all done with those clusters, the centers of those clusters are referred to as visual code words. So here you can see all of these images that were taken from something like tires, then they were all clustered, and so the code word is this little tire piece. Here is a centered tire, right? This is a piece of a tire, this is a full tire, and there are other kinds of code words. So these become the little features that we're going to look for in different images. And this, of course, would assume, in this particular case, we're looking for cars. We've got a bunch of training images on cars. By the way, I should say all of this is done automatically. Okay, so you're going to see some things that look a little strange in terms of code words. Well, it just happened to fall out of the data. This is not a human doing it. This is telling the system to go ahead and do this. The second thing you do is you take these code words, these are our features. Remember, like we had the tire, and we found everywhere that the tire landed in the image. So what we have here is all of these marks are these little interest points. And what we do is, for every interest point, we find the feature that seems to look best at that point. So that becomes the label of that point. All right? So remember, just the way we had a label before that said the gradient was horizontal pointing inward, here we have the label is that it's the bottom right-hand corner of a tire. Okay? So this is mapping each of the interest points to some particular patch. Finally, what we do is we take each of these little features and we treat them just like we treated those little gradient images, all right? We take the patch, we find the displacement vector to the center, and we write down that displacement vector in a table that's indexed by a patch label. So if I find a tire and it's to the left, which means the displacement vector is to the right, I put down that displacement vector. If I find a tire to the right, which means its displacement vector is to the left, I add that same displacement vector to the table with the entry of the tire. And that stores all those displacements. So at runtime, it works like following. So here I'm going to show you on two cars using just the tire patch as the example. All right? Suppose we have only one feature, and it's the tire. And suppose we try looking for it everywhere. Okay? So we look for it everywhere, and we find these four. Okay? Well, when we find them, what we have to do is we have to take the displacement vectors associated with that code word and vote with all those displacement vectors. So let's remember, for the tire code word, there are two displacement vectors, one to the right, one to the left. So we vote for those. And then we simply look for points that have more votes than other places. So in this case, where are those points? Well, just in the center of the cars. As I said, this was originally proposed by some folks at the ECCV, European Conference of Computer Vision, 2004, and it's subsequently been evolved from that. And so the idea is that we're now using this notion of detecting features and something about their configuration in order to try to find these objects. So that's the end of this lesson, and it's the end of our entire discussion about Hough transform. It's an interesting example of a general approach. In this case, it's voting, that was first developed many years ago, like I said, back in the 80s, which resurfaces in sort of more sophisticated forms as things come along. In fact, there's something recently called Hough forests. And Hough forests combine the Hough offset ideas that features vote for offsets with an ensemble or a collection of classifiers similar to random forests, and that's why these things are called Hough forests. Fortunately for you, you're only going to be using the basic Hough transform for lines and circles for your problem set. It's more work than it looks, so make sure you leave plenty of time. And I think after you get that working, you'll have an appreciation for what it means to get these more sophisticated methods to work. All right, welcome back to computer vision. So let's see. So we did the images as functions for a little bit and started talking about edges, and then we took a little bit of a detour where we talked about Hough transform in terms of extracting information using those images as evidence. So now it's time to get back just a little bit to image processing. And this lesson and one more or maybe two more beyond this, we're going to be talking about what's called frequency analysis. Now in the old days, that is, and that's actually pretty old already. Now we're talking 40 years ago, 30, 40 years ago, all of you who would be working on images, you would actually have been electrical engineers. And you would have spent a lot of your time studying this stuff that we're going to be talking about extensively. You define your filters and other types of image analysis operation in terms of what's called frequency response. That is how things change when you have high frequency stuff and low frequency stuff. But most of you are much more oriented to computer science, where we tend to think of images as data structures and not so much as a signal. But some of this understanding is still critical. This is especially true for a phenomenon referred to as aliasing. I know many of you are familiar with aliasing in a sort of image perspective where you see the little jaggies because you've got a line that doesn't go perfectly straight. But it's actually a frequency phenomena. And in fact, the goal of this lesson and the next few is to get to a point where you could talk about aliasing from a frequency perspective. And it'll teach you why, for example, if you have an image and you want to make it half the size, you shouldn't just throw out every other row and every other column. That's the wrong thing to do. And by the time we're done with this, you'll see sort of why that's the case. Here's a picture, a very famous picture, and the question is, what do you see? All right, so most people probably first see the kind of stylistic drawing of a naked woman, and then maybe if you look, you'll see down here, there's a picture of Abraham Lincoln. But if you take a look at the title of the picture, this is a painting by Salvador Dali, and it's Gela contemplating the Mediterranean Sea, which at 30 meters becomes a portrait of Abraham Lincoln. Now, you don't actually have to step back 30 meters. We can just blur the picture. And when I blur the picture, it looks like that. And aha, there's Abraham Lincoln. And so the question is, what's going on there? All right? And loosely, the answer is that at this image, there's all this high-frequency information that's showing you all these squares, and you see the outline of the woman, and you can see what she's looking at, something in the distance, and you can see that picture of Abraham Lincoln. But at the low frequency, it actually is a reasonable picture of Abraham Lincoln. And the idea is that images can be, actually any signal can be decomposed into a set of things that describe it. And we're going to get to frequency, but really what we're talking about is what's referred to as a basis set. So what is a basis set? So here we've lifted this from Wikipedia, edited a little bit. So a basis set, B, well, you have to talk about a vector space. So something is a basis set of a vector space, V, is a linearly independent subset of V that spans V. So let's expand those words out just a little bit. So let's suppose we have B that's just these vectors V1 through Vn, and it's just some finite subset over this field. So a field comes from mathematics, but let's just talk about the real or complex numbers. Okay, then a basis set B if it satisfies the following conditions. So linear independence, okay, basically means that if I have some different constants, A1 through AN, so these are constants, If I take a constant times each of the vectors, and I've got a different constant, and if the sum of those is 0, then it has to be the case that all of those constants were 0. This is no different if you think of this in 2 dimensions. If I have 2 vectors that are not in the same direction, then if I combine them, right, I get this answer like that. Well, the only way that distance can be 0 is if both of the coefficients are 0. So that's linear independence. And then there's what's referred to as the spanning property. Okay, that, remember, it spans this vector field. And what that means is that for any vector in that vector space, I can create it by just some linear sum of the basis set. And again, you know, basically the idea is, so we normally think of a basis set as being perpendicular, but it doesn't have to be, right? So if I've got this and I've got that as my 2 basis elements, and I want to create a vector that's like that, then basically what I have to do is I have to take some multiple of the horizontal plus some multiple of the vertical will get me to that picture. By the way, most of you are used to basis sets being orthogonal, okay? So, you know, x and y. All we said they had to be was independent, okay? Now, it's helpful if basis sets are orthogonal. We'll talk more about it in a minute. Because what it means by orthogonal is, in order for me to figure out how much of the x there is in a vector, I don't have to worry at all about the y, because the y amount doesn't affect the x amount because they are orthogonal. Another way of saying that is if I take a vector and I take a dot product with the x direction, I get one value, and a dot product in the y direction, I get another value. Well, if I take each of those dot products times their basis vector and sum them up, I get back the new vector. And that's just because x and y are orthogonal. And that's why it's helpful if your basis sets are orthogonal. But technically they don't have to be, they just have to be independent. That'll let you reach any vector. If we had a basis set for images, and we'll talk a minute about what that means, that could be probably useful for analysis, especially for linear systems, because we could consider each basis component independently. Why is that true? Because remember, in linear systems, things just sum. So if I could say how some operator applies to each element of the basis set, and then I just have to scale it and sum it, then I know how this operator applies to the entire image. And that's part of the reason that we're going to go through this whole basis set decomposition, is because most of our operations are going to be, that we'll be considering, are going to be linear operations. And when I was talking about things from a long time ago in filter theory, etc., those are all based on a linear types of operations. To consider basis sets of images, what we're going to do is we're going to think for now of an image as just being a single point in a very large space. So if I have a space that's an n by n image, right? So let's suppose it's 100 by 100. So 100 by 100, that's 10,000, okay? So you can think of the entire image as just a 10,000 dimensional vector. If you wanted, that would be fine. Okay, so what would be a basis set for a 10,000 dimensional vector space? Well, one particular basis set is just our usual one, right? We do zeros, except we have a 1 in one of the elements. That's like x and y and z and p and q and r, and you run out of letters before you get to 10,000. But basically, you have a 1 in every place. Now, are these independent? Yep. Because if I sum up a whole bunch of them, the only way I can get to a 0 vector is if I have a 0 multiple of each of them. Because they're independent, they don't affect one another. But it's really not a very helpful basis set, because each one of these basis vectors, that one, that's just a single pixel. So telling me about sort of how it behaves with respect to a single pixel, that's not a particularly helpful basis set. Instead, we're going to look at a different kind of basis set. And it's a basis set that considers this image, or any image, in terms of how quickly it varies in different directions. So here you see an image that is just, no variance at all, so you can think of that as just a constant intensity. And as you move to the right, it starts to wiggle faster and faster and faster. As you move down, it wiggles faster and faster and faster, but this time horizontally. And then if you combine them, you would get these different orientations. And by the way, the two different pictures of the blue and the green are sort of, you can think of these as like kind of like sines and cosines, kind of offset. Now this particular basis set has a name, okay? And it's referred to as the Fourier basis, or Fourier decomposition. And it's named after this dude, Jean-Baptiste Joseph Fourier. okay? So he had a crazy idea in 1807, that any periodic function, that's a function that repeats, could be rewritten as a weighted sum, try to say that quickly, rewritten as a weighted sum of sines and cosines of different frequencies. In other words, you could make any repeated pattern, doesn't matter what it looks like, as long as it eventually repeats, using sines and cosines. So don't believe it? Well, you wouldn't be alone. Back at the time, there were some other folks you may have heard of, like Laplace or Poisson and other mathematician types. They didn't believe it either. A lot of controversy. There's a question about whether Fourier's proof was correct. Turns out his result was correct. And in fact, it was so controversial, it wasn't even translated into English until 40 some odd years after his death. But like we said, it is true. And the series now that he's dead and famous, we call this the Fourier series. All right? We're going to get from Fourier series to Fourier transform to discrete Fourier transform, just so you know where we're headed. The idea is that if you have a signal, the signal has as its building blocks these sinusoids. And if you add enough of them, you can get whatever component you want. So here we're adding up different, this was our target. These are the elements that we're adding. We're going to show this more in a minute. And this is the function that we're building up. So before we look at that more carefully, how many degrees of freedom are there in this signal right here? Okay? There are 3 degrees of freedom. What are they? Well, A here is just going to be amplitude. That's going to be a scale. All right? And then there are these 2 numbers, omega and phi. And omega is what's referred to as the frequency, and phi is the phase. So which of these is most important? Which of these encodes the notion of a coarse signal versus a fine signal? Well, it's going to be this one, the frequency. Right? So as you change that frequency, as that number gets bigger, essentially the thing wiggles more quickly. To give you a little bit of a notion of sort of frequency and time, et cetera, and pretty soon we're going to throw time away because we're only going to be interested in space, but since you talk about how quickly something wiggles, and it originally was derived from one dimension, we'll talk about it this way. So here I have a signal, okay, g of t, okay, that's made up of 2 parts, okay? It's got a sinusoid of some frequency f, and then another sinusoid of 3f, but it's been scaled to make a third. So that's this signal here, and you can write that as just the sum of these 2 sinusoids. After all, that's what this equation says. And because of linearity, the stuff just sums, the combination of the 2 on the right gives you on the left. And if I were to draw out sort of the contributions of the sinusoids to the signal, it would look like this. Okay, so this is written in this particular way. I'm only showing you positive frequency. We'll talk about negative in just a minute. But whatever f is, the idea is that the signal here has a frequency spectrum with a certain amount of power at f and sort of 1/3 of that at 3f. Okay, and this is one form of drawing out the spectrum. We'll talk more about spectra in just a minute. You'll notice that this picture on the left is sort of kind of approximating getting towards a square wave. And it turns out that actually, if you really wanted a square wave, what you do is you keep adding these odd frequencies, all right? And I want to show you this because sometimes people will ask, well, how can I get sort of a sharp boundary using just smooth sinusoids? So here we have our original picture, and now I take that original one and I add in something that wiggles at 5 times f, and you see that I'm getting closer yet to a square wave. And then I get to 7 times f, and what comes after 7? 9. And what you can see is that we're getting closer and closer to having this as a perfect square wave. Okay? And in fact, you can show that a square wave can just be written as this infinite sum, okay, of these frequencies. Okay? And the amount of power you need goes down as the frequency increases. All right? So what we want to do is we want to get to a point where we can look at a signal and say, process it in a certain way or compute with it in a certain way to say, what are the sinusoidal components that go into making up this image? And in fact, you can show that to do a square wave like this, you need an infinite sum of decreasing amount of increasing frequency, and that's what's shown here. Now, what I haven't done is I haven't talked to you at all about phase. And in fact, I'm not talking at all about, what the phase, right? I could have this offset or I could have different elements offset. And in fact, all I'm showing you here is the amount, or you can think of it as the power, we'll talk more about that in a minute, of the content of each sinusoid. And the reason we're not talking about phase is Our goal is not to reconstruct an image. We just want to, typically what we're going to want to know is how much power there is in each of the different frequencies. In computer vision, we're interested in sort of analyzing what's going on. If we're actually going to reconstruct images, then we would probably have to worry more about the phase to get you better reconstruction. But we're not going to do that today. Given this idea that any signal, certainly any periodic signal, can be made up of a sum of sinusoids, we're going to start to move from just this notion of a series to notion of a continuous signal, and we're going to talk about something that will allow us to know how much power of any given frequency there is in an image. That is, we want to transform our image from just something that's, or our signal, that's something a function of time or just of space, to know what it is in terms of its frequency. And that transform is called what? It's called the Fourier transform. And now we're going to, so we did Fourier series, then we'll go to Fourier transform, and then we'll go to discrete Fourier transform, which will get us to that image stuff. All right? So we want to understand the frequency, and frequency is usually written as omega of our signal. So we want to parameterize, we want to transform our signal instead of by x, which is in space, by omega. And we do that by what's known as the Fourier transform. And the Fourier transform is going to take some spatial signal out, and it's going to give us some properties that encode both the phase and the magnitude for each given omega. Okay, so we need the phase and the magnitude for each given omega. Specifically for every omega from 0 to infinity, and by the way, it's actually from minus infinity to infinity. The idea is that f of omega holds the amplitude and the phase, all right, of the corresponding sinusoid. So this f has to have the amplitude and phase. How can f, a single thing, hold both amplitude and phase? Notice I didn't say a single number. Because remember, f of x is just the value of f, right? So it's a number. F of omega is going to be amplitude and phase. How do we do that? Well, f is actually, the capital F is actually a complex number. Now, hopefully you remember something about your complex numbers. If not, I'm going to give you a really, really brief review. Okay? So basically, f of omega is made up of two parts, a real part and then what's referred to as an imaginary part. Okay, so remember a plus bi? Okay, well in this case it's the real part of omega plus the imaginary part. And you may remember that the magnitude of a complex number is just the square root of the sum of the two elements. Normally with square root a squared plus b squared, so here it's the square root of the r squared plus the I squared, and r is for real and I is for imaginary. And the phase, the relationship between these, is going to be written this way. Okay? It's the arctangent of the imaginary plus the real. And the thing that's missing here is the idea that the real part is going to be due to the even function, and the odd part is going to be, and the imaginary part is due to the odd. And all that means, if I have a function here, this is my cosine function, all right, and that's even with respect to the origin. That is, it's symmetric about respect to the origin. The sinusoid, and I'm going to screw this up, right? Yeah, because it has to come here and then be there, and then, so it has to be 0. There we are. That's my sinusoid, because it has to come down to 0 when that thing is high. All right. It is odd. That is, sine of negative x is minus sine of x, whereas cosine of negative x is equal to the cosine of x. So the bottom line is that this part, is the real part is going to be the cosine part, and the odd and the imaginary part will be the sine part. When we do a Fourier transform, all we're doing is computing a basis set. And I'll show you what I mean by that. See this ugly, ugly integral here? Okay. What I've got is I've got the sine of one function and the sine of another, two different frequencies, a and b. Okay? And then I'm integrating this all the way from minus infinity to plus infinity. And I claim here that it equals 0 if a does not equal b. Now, why is that true? Any guesses? Well, let's just think about this intuitively, right? If I have some sinusoid, and now I've got to do one of a different frequency. That's easy. Boy, that's beautiful, huh? Essentially, at some point when this is positive and this is that same positive value, I'm going to try to find, hopefully there's some positive, I have to make one up. Yeah, let's pretend the red thing went down here like that a little bit, right? That when the red is same positive, the yellow was the negative of it. So the product of those two numbers and then sum together is going to cancel each other out. And That's sort of a hand-wavy way of saying that this entire integral is going to be 0 as long as a does not equal b. But you might ask, what happens when a does equal b?
What happens when a does equal b?
Let's start with assuming that they're in the same phase, exactly the same phase. Well, then it's just sine squared. Sine squared is positive. Sum that over infinity, what do you get? You get infinity. And so if you have two sinusoids that are the same frequency, you'll get an infinite value unless they're perfectly pi over 2 out of phase, in which case it's going to be 0. In other words, sine times cosine go. But the bottom line is, the way of thinking about this is that if I integrate a function, if it's made up of a sinusoid that's different than omega, when I take the sine of omega and I do that full integral, I get nothing. But if it's equal to that sine, I would get infinity. And that's going to be written like this. So let's just do a simple example. Suppose I've got a simple function. F of x is cosine of 2 pi omega x. All right? Well, then, let's pick some frequency, and we'll call it u here, just keep things simple, right? If I take this integral, okay, that's going to be infinite if u is equal to that same omega, all right, and it's going to be 0 otherwise. So that looks like this, okay? So we just have these two, remember impulses? We just have these two infinite spikes here, and that's referred to as an impulse that corresponds to the cosine. You see that they're positive this way, and that's because it's cosine. If it was sine, because sine of negative x is negative sine of x, that would look like it would be up here, and that would be down there. That's what the sine is, okay? That's kept as the imaginary part. So we're just computing a basis set of saying how much of this sinusoid is in there, all right? And we can do that for all frequencies. But then you might ask, well, don't we also have to do it for all phases?
Don't we also have to do it for all phases?
She studied that one. Well, the short answer is no. One of the cool things is if I have cosine of omega x and I have sine of omega x, right, so one is 90 degrees or pi over 2 phase out of phase, I can make any phase by a linear combination of those. You can show that, it's just true, we can do a little demo, but basically if I have a sinusoid of any phase, if you just tell me sort of what its integral is with respect to cosine and what its integral is with respect to sine, I can tell you what the phase of that sinusoid is. Doing this a little bit more formally, so we're going to represent our signal as an infinite weighted sum of an infinite number of sinusoids. So the Fourier transform, here it is in its beautiful glory in one dimension, okay? F of u is the Fourier transform. We just take the infinite integral of the original function times e to the minus I 2 pi ux. And you might say, what? Where did that e to the minus I blah, blah, blah come from?
Where did that come from?
Oh, she didn't fall into that trap. Well, again, remember from your probably calculus class somewhere, e to the ik is cosine k plus I sine k. That's why this is the even part and that's the odd part. This is where I is square root of minus 1. By the way, if there are any electrical engineers out there, they have j as being the square root of minus 1. I don't know why, because mathematicians use I guess electrical engineers didn't like the mathematicians. We're going to use I. So what the Fourier transform does is it converts from the spatial domain into the frequency domain. And the frequency domain is either written as omega, sometimes as u, as we're doing here, sometimes even s when you're talking about Laplace transforms and stuff like that. But the idea is that this cap f is the frequency spectrum, or I should say it's frequency of f of omega. And we're going to talk about its magnitude in a minute, which is going to be sort of what when we refer to as the spectrum. Just for completeness, by the way, so here we had the Fourier transform. This is the inverse Fourier transform. Unsurprisingly, if you tell me what all of the sinusoids are, if I sum them all up, okay, at some location x, and I sum up over all the sinusoids, I can recover the original signal. And that's called the inverse Fourier transform. So putting those equations we just saw sort of into some simple pictures, our frequency in general can be thought of going from minus infinity to infinity. And the real part is the cosine part and its impulses that look like this. The imaginary part is the odd part. That's the sine. Looks like that. And as we said before, typically we're only going to worry about the magnitude of the power. And so you just take the sum of the square, square root of, and this would be the power. When I combine the real part and the imaginary part, to make power, I can then take a look at the power spectrum of different kinds of signals. So here's some, and I apologize for sort of the terrible picture. So here we have just a sinusoid, and our sinusoid just has power at those two peaks, right? Regardless of the phase, the sum of the squares, square root of, is going to give us those two peaks. And also, here we have that square wave, and you can see that the power falls off as frequency goes up. And that's what we showed before. And one of the interesting things also is if you take a signal out of some sort of typical natural image or typical natural signal, you take a whole bunch of them, you also tend to find these spectra falling off. And that just is a property of how images are formed by looking at things in terms of natural images. Let's just talk about a couple of limitations on this, which are going to get us to the Fourier series in just a minute. Okay. For this integral to exist, this Fourier transform, we don't actually want infinites, right? Because that's not so good when we try to like write down infinity. It just goes a really long time. All right. One thing we could say is that this whole thing is integrable, okay, if the original function itself is integrable. That is, if I take the function, I actually take its absolute value. If I sum it up from minus infinity to infinity, it can't explode. It has to be limited to a value. So you might ask, but wait a minute, I thought we had infinite repeating series.
I thought we had infinite repeating series.
We did when we were talking about Fourier series. We're now talking about the Fourier transform, where we're trying to keep things bounded. So the idea is that these integrals have to exist. It's based on the same principle, but it's this idea. So in Fourier series, we talked about repeating functions. In Fourier transform, we're talking about integrable functions. All right. In a minute, when we have a fixed length function, it'll be clear. In fact, let's get to that right now. You see, it says so. Obviously, if there was a bound of width t, right, so if all my entire function fell within t, then obviously I could just integrate from sort of t, negative t over 2 to plus t over 2, right? That would be the entire integral. And that's going to lead us, at least in my twisted mind, to this notion of the discrete Fourier transform. The discrete Fourier transform is what we have to do when we want to start doing things in computers, because after all, we don't have continuous signals, we only have discrete values. So the discrete Fourier transform is written as this. Now we say f of k, where k in this case would be the discrete frequency, all right? And what we're going to do is we're going to sum over all the pixels, so we're having x going from, or signal in 1D in this case, from 0 through n minus 1 if I have a total of n of them. So there's this 1 over n out here. And now we have this e to the minus I, and you see how it's k over n? Because basically, instead of now thinking of frequency as how quickly it wiggles in terms of time, it's sort of how quickly you wiggle over the entire length of the image. So k is written as it's the number of cycles per period of the signal, or per period of the image, right? Cycles per image. This only makes sense essentially from 0 up to n over 2. Why only n over 2? Well, think about how quickly a sinusoid could possibly wiggle in a image that has n pixels, right? Well, it would go white all the way to black, all the way to white, all the way to black, all the way. So that would be a period of 2. So the frequency, the number of cycles, would be n over 2. So basically, k can only go from minus n over 2 to plus n over 2, because that's the highest frequency you can have in a discrete image. I've been showing you this in one dimension. It extends pretty simply in 2 dimensions. And here are the 2-dimensional forms, okay? So this f of u, this is just when I've got a continuous 2-dimensional function. Here we have f of xy. Well, when we do it in discrete land, f of xy is now going to be at discrete points. And then we have f of kx, ky, those are the 2 different frequencies. The discrete frequency in x, the discrete frequency in y. And by the way, this works in the middle. If you put the origin of k in the middle, you want to put the 0 in the middle, so from minus k, n over 2 to plus n over 2. Let's take a look at applying this 2-dimensional discrete Fourier transform to images. So remember, we talked about that we're going to have these bases that have horizontal, vertical components and can be combined. What does that look like when we apply these things to images? So let's take a look at some very simple examples. All right, so here I have a sinusoid, and it's at some particular frequency, and it's only made up of vertical stripes. What is the spectrum, the power spectrum of its Fourier transform look like? Well, it looks just like this, and it's a little hard for you to see, but there are two bright dots there. The origin is here in the middle, and there's a dot to the left and a dot to the right. Okay, those are my spikes for the frequency of this particular sinusoid. So this picture, you see, has only horizontal stripes, and it varies more quickly. So these dots are now spaced vertically for a sinusoid that goes in this direction, and they're further out because the frequency component is higher. If I have a sinusoid in an oriented direction, same deal again. It's a little hard to see. We've got these dots that are spread in that direction. Let's go back to our linearity. So let's suppose I take the picture on the left and the picture in the middle, and I sum them together. And we're actually going to do a sum, so it's linear, right? So this picture is going to look like that, so it's some combination of sinusoids. But remember, a Fourier transform, a Fourier series, is just made up of sums and multiplies. It's a linear operation, okay? So the Fourier transform of the sum is just the sum of the Fourier transforms, okay? So that's why this picture is just these combined. So let's take a look at some spectra of some real images and some examples, okay? So here's one. Now, if you remember, this is Lena from way back in 1972, and this is no relative of Lena whatsoever, okay? You'll notice that just looking at the image, there's a lot of power in the middle, and then stuff falls out towards the edges. And that's, like I said, it's often the case that natural images have similar power spectra. And what really matters for reconstructing the image would be the phase. We're not doing reconstruction here, we're only looking at the magnitude. So suppose I wanted to get rid of the high frequency content. Well, here's what you could do, and we'll talk about using the inverse Fourier transform next time. But I could take Lena, I could take her power spectrum, I could remove all the stuff out here, and then I could reconstruct it. You can see that there's all these ugly lines in here, okay? That's what's referred to as ringing. This ringing happens because this actually doesn't have any high frequency at all, but you actually needed the high frequency to smooth out those little edges, okay? And so when I remove them, I end up with having just these little ripples, and that's referred to as ringing. And here's an example of doing the other thing. We take Lena, okay, we remove the stuff out of the middle, so you can see this thing, zeros there, and you'll notice that what's left here is essentially an edge image. And if you think about that, the high frequency components are giving you where the edges are. Okay, and we'll also look a little bit more about that when we talk about aliasing. A couple more things real quick here. You remember our sharpening filter? So our sharpening filter sharpened the image by subtracting, by giving you twice the original image minus a little bit of blurring. So what's happened here is this is our Lena again, and if you compare this one to this one, you'll notice that there's a little bit more bright stuff out here than there was there. And you'll notice that this picture is in fact sharper than that picture, and that's because we've accentuated the high frequencies. And one more here. So here's a cool texture. Here's our brick texture, right, that has mostly these lines here, but a few of these there. And what you can see is you basically have just the verticals here, horizontals there, okay? And then this picture, okay, you've got all these angled lines, and that's what's showing up as all these angled sinusoids in here. Let me show you just one more example just to highlight a particular little problem. So here we have a nice man-made scene of some beautiful bridge somewhere in Europe. And you'll notice that there is this strong vertical here. And a vertical, if you think about it's coming down this way and coming that, is a step edge horizontally. Okay, remember, dots like this are sinusoids that vary as you go up and down. And you remember that if you have a step edge, remember we had a square wave, okay? It had all the frequencies just in decreasing power. And what you're seeing is a whole bunch of frequencies in decreasing power coming down. So the question is, where is the strong horizontal edge that's suggested by that vertical line? Remember, a vertical line is all of these frequencies, which means that it's got a horizontal sharp edge. And the answer is a little tricky. Basically, if you think about how the sinusoid goes in the image, it's essentially as if it assumes the image just kept wrapping around. Okay, remember we talked about the Fourier series, assuming that everything just kind of repeats. So here what we're essentially doing when we do this sum from minus n over 2 to n over 2 is we're assuming that the thing continues, that it's periodic, which would mean that the thing over here should be the same as the thing over there. And if it's not, that would represent a significant change. And this edge down here is really different than that edge down there. So when you wrap it around, you get a big step. And that's what's causing that sort of weirdness in the Fourier transform. Do you remember when we were talking about doing filtering in MATLAB? There was a wrap option to head out off the edges instead of replicate or reflect. You could take the stuff from the top and put it back down on the bottom. And I said that won't make any sense to you at all until we get to Fourier analysis. Well, that's as if you had a periodic signal. Because if you don't have that, you get this funny sort of sharp edge. One way to eliminate that when you're doing Fourier analysis is you'll take your image and you'll multiply the whole image by a Gaussian that tapers off towards 0 by the edges, and then everything becomes nice and smooth. When in doubt, fix your life with a Gaussian. That ends the first lesson on frequency analysis and gives you some relation between sort of what's in the image and the frequency components in it. Next time what we're going to do is we're going to talk about how filtering and convolution are expressed in the frequency domain, and that's how it'll allow us to get to aliasing. I'll also say if you didn't follow everything that just went through, that's okay. I really just want you to sort of stay focused on this idea of frequency and the Fourier transform, and then as a way of getting the different elements, and then I'm going to show you how the frequency transform relates to sampling, or I should say frequency domain relates to sampling, which will get us to aliasing. All right, welcome back to Computer Vision. We're going to continue our discussion about frequency analysis and how to study images with the notion of frequency components. If you remember last time, we talked about the idea of decomposing images based upon frequency. And we motivated it by showing you this picture. This is that famous Dali picture, which when you allow the high-frequency imagery in there, you see a picture of a woman admiring the Mediterranean or something like that. But when you blur it, that is when you remove the high frequency, you just have the low frequency, it becomes a picture of Lincoln. And this idea of how do we decompose images into thinking about what was going to be a basis set that involved frequency. And the idea that a basis set was going to be some set of functions that were going to linearly span our possible signal. So the idea is that we should be able to make any possible signal out of this set, and that they are linearly independent, so which basically allows me to do this summation. We're also going to end up with an orthogonal basis set, so that when you change the amount of one basis element, you don't get any change in the others. And the basis set that we were talking about was this Fourier set, right? And the Fourier set basically decomposed things into sinusoids, and they were sinusoids here of increasing frequency that were sort of moving vertically and horizontally. And the idea is that we could construct images doing this. So related to that idea was this notion of what we call the Fourier transform. And the Fourier transform was that you would put in a signal, showing it here in 1D, but also talk about in 2D, and what you would get out was, instead of f as a function of x, that is the intensity as a function of location, you got out a cap f as a function of omega, where omega was frequency. And the idea is that cap f would decompose into an even component and an odd component being represented by complex numbers. And so this would allow us to represent both the magnitude and the phase for a given frequency. And if you wanted to, you could recover that magnitude and phase. The magnitude is just the square root of the sum of the squares of each of the real and imaginary component, and the phase was just this arctan of this relation. To do the Fourier transform, it was represented by this sort of ugly-looking integral. Here I'm showing it to you in 1D. We'll do it again in a minute in 2D. But the idea was you took your function and you integrate from minus infinity to infinity, and you multiplied it by sinusoids of whatever frequency, and sometimes frequency is omega. When we're going to do it for 2 dimensions, it's u and v, so here it's written as u. And even though this does not look like a sinusoid, you had to remember that e to the ik was cosine k plus I sine k. So this is what allowed us to go from the spatial domain to the frequency domain. We also mentioned that you could inverse this if you wanted to, right? So if you give me the Fourier transform f of u of a signal, there, by just changing whether that's plus or minus, I could do the integral and get back the original signal. But now we have both u and v. We also talked about the discrete version, and we showed some examples here where you're taking these sums instead of the integrals. And most of the time, we're mostly interested in the power. Remember the square root of the sum of the squares? And that's represented here. So I might have a signal that has a certain amount of even part and an odd part, or the real and the imaginary. You take the square root of the sum of the squares, and you got the magnitude. And the magnitude of the power is what we'll typically be talking about when we talk about the presence of frequency within a given image. We want to know the power of it. The phase is important for doing reconstruction, but in general, we're not going to be doing reconstruction. So today, what we're going to do is, in this lesson, is we're just going to relate the Fourier transform to convolution, and in particular, how convolution in space is multiplication in frequency. Let me show you how that works. Let's suppose we have a function, g, which just f convolved with h. Maybe h is a filter, f was the original image. Doesn't matter. It's f convolved with h. And suppose I want the Fourier transform of g. All right, well, that's going to be written as follows. Okay, our definition, right, g of u is just the Fourier transform of g of x. But g of x is just the convolution, so that's sort of in here, this part here, of f with h. Remember, that was my definition of g, the convolution of f with h. What I can do is I can rearrange this, and you'll see what I did here was, this was ux, so here we have u tau, and here we have x minus tau. All right, and so if you multiply those together, you would just get ux, so it's the same thing. But I've rearranged it so all the tau stuff is here, and all the x stuff is there, with this tau in there. And so we're going to make a quick change of variables, right? I'm going to say, let's define a new variable of x minus tau is x prime. So now I'm just converted that to x prime. So now I've got one integral here, and one integral there. And if you stare at those and you ask yourself, get ready, what are those integrals?
What are those integrals?
Well, what are those integrals? Well, let's take a look at just this integral. That's the Fourier transform of f, right? I happen to use tau instead of x, but it's the same thing. This is the Fourier transform of h. So that can be written as just fu times hu. Megan laughed when I said fu, by the way. So g of u is just fu times h of u. In other words, remember, g was the convolution of f with h. G of u, the frequency domain, is just the product of the Fourier transforms of f and h. Okay? So the idea here is that when you do convolution in the spatial domain, you're essentially doing multiplication in the frequency domain. And this is going to be really important for the next lesson when we talk about aliasing, and also for what we're going to talk about here in terms of how convolution does frequency manipulation. So this is just written here, is that if in the spatial domain I do convolution, in the frequency domain I'm doing multiplication. Also, by the way, because of the symmetry of how the transforms work, if I were to multiply in the spatial domain, that is, if I took two functions and I multiply them together, I don't convolve it, I just multiply them, the Fourier transform of that new function is going to be the convolution of the Fourier transforms of each of the individuals. Okay? We're going to make use of that both here and a little bit when we talk about aliasing. So in the spatial domain, you do convolution. In the frequency domain, it's multiplication, or vice versa. That actually means that, and this was more important a little while ago, but people still use it today, if I wanted to, let's say, do a convolution of a function with some really big mask, which is generally an expensive operation, I actually could do it a slightly different way. All right, and that's shown here, right? Suppose I want g to be f convolved with h. But suppose f and h are both very large things. So remember, convolution is ugly because it's n squared m squared, where n is the size of the image, n by n, and m by m. Well, so what we can do is we could actually take the Fourier transform of f and the Fourier transform of h. And there are fast ways of doing Fourier transform called the FFT for fast Fourier transform, which we won't talk about. But I can do those Fourier transforms quickly. Then I can multiply those two Fourier transforms together to get the new Fourier transform. And then I can do the inverse Fourier transform to get back the answer. Like I said, this was really important when machines were slower. These days, people tend to work in the spatial domain. But even today, if you have a large mask or some large function you're trying to convolve against a large image, it's not uncommon to use the Fourier trick to do that. But we're not really going to talk much about doing this inverse part. Instead, we're going to talk about how the Fourier transform shows you what's going on in frequency. So suppose I have a function, and here's a function, and suppose this is this noisy signal. I want a nice smooth version of it, right? So how might I do that? Well, we learned before that you might blur it with, let's say, a Gaussian kernel. Okay, and what does it mean to blur it with a Gaussian kernel? We're going to convolve the underlying image with that Gaussian. But it turns out the Fourier transform of a Gaussian is a Gaussian. All right? And that's what this shows here. So the Fourier transform, if this is h of x, this is h of u, it's another Gaussian. But you'll notice that here it's over sigma squared, and here it's times sigma squared. Okay, and that's what this is trying to show you here, is that if I have this Gaussian kernel with a variance sigma squared, that I get a new Gaussian, and I apologize, this is an awfully drawn Gaussian. I get a Gaussian whose variance is 1 over sigma squared. Now, if you think about that, that makes a little bit of sense, right? First of all, let's think of a really, really skinny Gaussian, all right? Like almost an impulse. Remember when you convolve a function with an impulse, you get back the original function? So that means you basically keep all the frequencies. So if my kernel was a very tight little Gaussian, I would expect to be able to keep all the frequencies. I expect to be able to get almost all of the frequencies back. Likewise, let's suppose my kernel was really, really fat, blurs the heck out of everything. Well, then I would expect to get hardly any high frequency and only to get only the low frequencies. And that's why the Fourier transform, that's one way of thinking about that. The Fourier transform of a fat Gaussian is a skinny one, and the Fourier transform of a skinny Gaussian is a fat one. Remember, they go back and forth. All right. So what's going to happen when we blur this function with the Gaussian is we're going to multiply its Fourier transform by the Fourier transform of that Gaussian. And what it's going to do is it's going to keep the low values and it's going to lower down the higher frequencies. It's going to reduce the higher frequencies by doing that multiplication. And we say that that means that it attenuates. That's the word we use. It attenuates the high frequencies. So I can show you an example of this being done in 2D, that is with an image, here, okay? Here we have an original image, a beautiful little still life of some fruit in black and white. And here is its Fourier transform power spectrum, just the magnitude. So I'm not showing you the phases. The middle, remember we put the origin in the middle, is the low frequency. And you can see that it falls off as you get out to the outside. Now, we're going to blur this thing with a Gaussian. And I'm showing you this Gaussian here at the same scale as the whole image. So this Gaussian might be 15 by 15 pixels, but it looks really small because we have a good-sized image. But that would blur the image a little bit. And when I convolve the Gaussian with the original image, I get exactly what we'd expect, a slightly blurry version of the image. But look what happens in Fourier space. The Fourier transform of this tight little Gaussian is this big fat Gaussian. Remember we said small Gaussian in space has a big Gaussian in frequency. And then we multiply this times this, and what that's going to do is it's going to keep the areas in the middle, which you see here, but it's going to attenuate the areas on the outside. So it reduces those low frequencies. And in fact, if I had wanted to, in order to recover this image, what I could have done was taken the Fourier transform here, multiplied it by this one, gotten this, and recovered back. Except that to actually do the recovery, it wouldn't be enough to just look at the magnitude. I would actually have to keep the real and imaginary parts. I'd have to keep the phase of the transform. But here I just wanted to show you what happens to the different frequency power. We've actually looked at this just a little bit before when we introduced the notion of frequency. So here we have a picture of this, we did have this picture, this man-made scene, all right? And here what I did was I took the inside part and I set this all equal to 0. So instead of tapering it off like a nice Gaussian, I was ruthless and I set all of the frequencies outside a certain diameter to 0. So there's no high frequency component at all. And what you get is this ugly looking thing called ringing, all right? So this actually has low frequency, but because of some slight variations in here, it can't cancel them out with higher frequencies that it needs. Okay, so what gets left over is what's called ringing, and that's what happens when you clip the frequencies precisely. And I'm going to make that mathematically better defined in just a minute. The flip side of that is if I remove just those center frequencies, and I think in the image processing world this was called coring, where you pull out that center, all that you get left with is this high frequency bit, which is a lot like what? The edges. Okay, we know that there's this relationship between frequency and edges. At the high frequency is where you get these steep derivatives. All right. Let's continue looking at this relationship between the spatial domain and the frequency domain. Here are some simple properties of the Fourier transform. We started with one that we already talked about. Everything is linear because we're just doing sums and multiplies. All right. The one we just described was this convolution one, that convolution in the spatial domain is multiplication in the frequency domain, and vice versa. One that's kind of interesting is scaling. So if I scale a function by a constant a, so let's think about it this way. Suppose a was greater than 1. Let's suppose a was 2. All right? Well, that would mean that when x had been 1, now x is 2, so it would shrink, right? When you multiply by a number bigger than 1, right? So if I had some function, right, now what happens is this value gets moved over there, so I essentially shrink that function, okay? So when I shrink a function, things are going to now wiggle faster, right? Because they were wiggling slower before. If I pull it in, it now wiggles faster. And so what happens is I end up stretching the Fourier transform. And this is the formula for it, 1 over a times f of u over a. So it's got that inverse property, which is just like that Gaussian idea also, right? If I make it fatter, my Fourier transform gets skinnier. One last one to look at, and we're not going to use this much, but I wanted you to see this, is when you take the derivative of a function, so this is some nth derivative, you multiply its Fourier transform by a function that's proportional to the frequency. So suppose n was just 1, you're taking the first derivatives, right? What that says is that you would be multiplying f of u times u, which means the higher frequencies get accentuated, which was exactly what we saw when we took derivatives. Remember when we added noise, high frequency noise, and then we took the derivative, the whole thing blew up? That's because you were multiplying it by, when you take this derivative, you multiply the high frequency components. If you take a look at Rick Zalewski's book, which we mentioned earlier, you can see a whole bunch of Fourier transform pairs. For example, the impulse, which is drawn like that, has a Fourier transform of 1. As we said, that makes sense because the impulse, when you convolve it, just gives you back the original function, so it better keep all of the frequencies. Likewise, we said here that the Fourier transform of a Gaussian is another Gaussian, but again, g of sigma goes to 1 over sigma. So fat Gaussian in space, skinny Gaussian in frequency. But look at this one. If I have a box filter, which is just a filter that's shaped like a box, it produces what's called the sinc function. Okay, and that's drawn here. And let's look at that a little more closely. Okay, so here in the spatial domain, we have our box filter, and this is our sinc function. All right, now sinc of x is sine x over x. All right. And you can think about that if you take the limit as x goes to 0, well, you remember L'Hopital's rule, take the derivative of the top, that's cosine. The derivative of the bottom is just 1, plug in a 0, it's 1. So the limit as x goes to 0 is in fact 1 right there. And then as x gets bigger, the sign gets attenuated, and that's what you're seeing here. So in other words, if I were to convolve something with a box filter, my frequencies are going to behave kind of in a weird way. You know, have this nice kind of low pass stuff, but then I'm going to have these various other frequencies that are going to get accentuated. And if you remember, we did that very early on when we introduced filtering. Remember, we convolved something with a box, with a square, and we said, man, is that ugly? This is why it's ugly. So you see this picture here, you see how it's got all these like striations? And I said, when we first did this, that that's because boxes aren't smooth and that we would make this more formal when we did Fourier analysis. Well, I made good on my promise, okay? The reason that when you convolve an image with that little square box that you see all this junk is because of this ringing here in the frequency domain. That's why we said what you should do is do what? Is you should apply a Gaussian, not a box. It makes a nice pretty picture, a nice smooth picture, because in the frequency domain you get this nice smooth Gaussian. One more thing about these sinc functions, okay? So we showed that the Fourier transform of a box is the sinc. Well, because of the symmetry, if I had a box in frequency space, that would be a sinc in the spatial domain. So what if I were to take some function, take its Fourier spectrum, and multiply it by that box? What would that look like? Well, I already just showed you that, right? This is essentially, it's sometimes called a pillbox because it's a box but in 2D. That is, instead of being just a particular width, it's a radius, right? So everything outside that diameter is set to 0 and everything inside is kept exactly. If you remember, the picture we got was this ugly picture with all this ringing in it. Well, now we know why. When you multiply the frequency by a box, it's as if you convolved the image with its Fourier pair over here with the sinc function. So if you take this pretty picture and you convolve it with this ugly beast, you get something that looks like that. And that's where the ringing comes from. That's why you never want to just cut out the high frequencies, because what you're essentially doing is convolving your image with a sinc function. That ends this lesson on the relationship between convolution in the spatial domain and the frequency domain. In particular, the convolution in the spatial domain is multiplication in the frequency domain. We've also made good on the promise of explaining some of these ugly artifacts that we saw. In particular, ringing is sort of the Fourier transform of a box. That is, if you cut off the frequencies hard, you get this ringing, or if you have a cutoff in space that's hard, you get this ringing in frequency. What we now have are the tools that will allow us to tackle aliasing. That is, when you do something to an image that involves sampling that causes it to look really ugly, and the high frequency stuff. It's a little bit of a bumpy ride, so strap yourself in and get ready for the next lesson. All right, welcome back to Computer Vision. This is going to be our last lecture or lesson or whatever this is on frequency analysis, and I bet you're happy about that because it's kind of off in the ozone of mathematics, and it's going to be hard to pull it back to the work that we'll be doing in terms of manipulating the images, but it's important. And in fact, today we'll finally get to the coup de grace, pièce de résistance. My French is terrible. What I really wanted to get to was the notion of how frequency explains the notion of aliasing. So if you remember, we've been talking about Fourier basis sets where we decompose things in terms of sinusoidal bases, and this is the picture we've been using to represent that. And then we talked about the relationship between convolution in the spatial domain giving you multiplication in the frequency domain. And we showed it with the math here. We said that if G was the convolution of some functions f and h, that we could derive that convolution in the spatial domain was multiplication in the frequency domain, and that was shown like this. And by the way, then this is really important for today, that multiplication in the spatial domain is convolution in the frequency domain. And you might ask, when do we ever multiply functions together?
When do we ever multiply functions together?
Today. It'll be some very special functions, but we'll do that today. We also showed some Fourier pairs. We talked about how the Fourier of a Gaussian is another Gaussian. We talked about an impulse is straight. We spoke about the box filter giving you this sinc thing that explained ringing and that like. But there's one other pair that I need you to know about, and again, we're not going to derive this, but it's important. And that is the notion of a pulse train or a set of impulses, okay? And so this is referred to as a pulse train. You can see that here. And the Fourier transform of a pulse train is another impulse train. And the thing that you need to realize is that, and remember, the scaling theorem gives us this, and a bunch of things give us this, right? As the pulses in space get further apart, the pulses in frequency get closer together. And this is a hand-wavy way of thinking about this. Imagine that our pulses got very, very far apart, okay? So far apart that I have an impulse in the middle, and the next one is infinitely far away. Well, that would be just like having sort of a single impulse. That's the hand-wavy part. Well, what is the Fourier transform of a single impulse? Well, we said it was a 1, because an impulse gives you back when you convolve it, it gives you back the entire image. So therefore, the frequency has to keep all the frequencies. So the hand-wavy way of thinking about this is, as I stretch out my impulses in space, I have to shove all these impulses in frequency and time infinitely close together to make a solid bar. Okay? And that's one way of thinking about how the Fourier transform of an impulse train is another impulse train, and as they get bigger in space, they get closer in frequency. So now we can start to talk about sampling and aliasing. So before we do that, we have to talk about the notion of sampling at all and the notion and the idea of reconstruction. So here we have the idea of some nice smooth scene illuminated by a light source, and then we have an imaging system that captures the intensity at a bunch of discrete places. And of course, what we'd like to do is we'd like to take the captures from these discrete places and be able to reconstruct this nice, smooth signal. That is, to know what that signal is. Let's talk a little bit about sampling. Sampling arises when we come up with this notion of how do you store a continuous signal in a computer. Right? So here we have a continuous signal, and this is in 1D, and we're going to do a lot of our stuff in 1D today because it's easier to draw. And so the obvious way of representing that, it's actually not the only way, because you can imagine different clever basis kinds of things, but sort of a normal way of thinking about that is by samples. That is, you just take the samples at each different location, and you write down what the value is. And once you have that set of samples, later what you want to do is reconstruct what the original signal was, right? And why do you want to do this? Well, maybe you actually want to use the signal. You want to play it, if this is audio, you want to play it through a speaker. And I don't need samples, I need a continuous voltage. Or maybe I want to do some sort of analysis or mathematical processing in terms of thinking about what this signal is. So essentially what you have to do is you have to guess what's going on between each of the samples. That's all you can do. You have the samples at discrete places, but you need to connect the dots, if you will. You need to fill in what's going on. And a lot of what we're going to talk about today has to do with what's actually going on when you think about taking a set of samples and then trying to guess what's in between. So to illustrate most of these points, we're going to use a 1D signal. So you can think of this like audio, all right? So here's an interesting audio signal. You see this signal? So this is time, okay? Goes this way. And it starts off with a low frequency and gets higher and higher and higher and higher and higher, and higher and stops. All right? If you were to play that sound, you would hear what's called a chirp. Okay, that's actually what it's called. It's called a chirp. It comes from radar, et cetera, whatever. It's something that has power in lots of different frequencies. So when you send a chirp out, no matter what the frequency response of the thing you might be hitting is, you'll get something back. It's also a nice way of being able to localize it. There are lots of good reasons to use what's called a chirp. But here's a chirp that has higher and higher frequencies. But it's a good signal to think about looking at aliasing. Continuing with thinking about the digital audio, we can think about sort of music or any other way of dealing with audio, right? When we record a sound, we have a microphone, and a microphone generates out a continuous voltage. By the way, you guys know how a microphone works? More or less, a microphone works the following way. We have a permanent magnet, and we've got an electric coil, all right, with some wires in it, and out of that coil comes another wire. And usually the coil is on a little springy mechanism. The permanent magnets are fixed. You speak, and that causes a pressure wave. A pressure wave causes the coil to move back and forth. when you move a coil of wire through a magnetic field, that induces a voltage. So that voltage comes out on that wire, and it's a continuous signal. But in order to encode this into a computer, we put it through what's known as an A to D converter, analog to digital converter, and we get out a bunch of samples. And then, by the way, in the old days, we used to put those samples on something called a CD, compact disc. You guys probably don't even buy those anymore. If you do, you only buy them to rip them. But basically, it's the set of samples, it's in a file, whatever it is, okay? When you go to play this thing, okay, what you do is you put your CD into your ancient CD player, it pulls out the samples, and then it goes through what's called a D to A converter, digital to analog converter, and then we take that continuous voltage and we put that out through a speaker, which, by the way, is almost exactly the same as a microphone, right? It's a coil of wire, you pump electricity through it, it generates a varying magnetic field, there's a set of permanent magnets that causes the speaker to move with respect to those magnets, and voila, out comes a continuous pressure wave. So let's talk about this sampling operation and then the reconstruction. So here we'll take as an example just a sine wave, okay? So I collect a bunch of samples. If I collect a bunch of samples, then what am I going to do to reconstruct it? Well, it might be enough to basically just connect the dots and get back the next sine wave, all right? And so as long as I had enough dots, that's easy enough to do. So I have enough dots, I connect the dots. But what if we missed things going on between the samples? What if we don't have enough dots? All right. Well, not surprisingly, something's getting lost, right? Some information is getting lost, right? So here we're showing you, right? So I've got a dot here, I've got a dot here, and there's all this change going on in between that is not realized, or I should say not captured. Perhaps the surprising result, though, is that actually this is indistinguishable from a lower frequency. Okay, so here what's drawn in is, this is the same set of dots that we had before, but there's a low frequency sinusoid that fits through there. Okay, continuing with that, with sort of the surprising result, is that the low frequency, that was always indistinguishable from those high frequencies if you only gave me a small number of dots. Okay, that is, I can't tell whether or not it's a high frequency or a low frequency. And that's the definition of aliasing. Or I should say, that's the example of aliasing. The definition is, it's a signal that travels sort of in disguise of another signal or of other frequencies. All right? Now, we're going to make this formal in just a minute, but that's what's going on in aliasing, is that I've got a signal and I can't distinguish between a low frequency that was in there and actually a high frequency. By the way, this also happens in time. Have you ever watched a video where an airplane propeller is starting to go, and then all of a sudden you start to kind of see it spinning backwards, and then you see it spinning forwards? Okay, airplane propellers don't spin backwards. They only go forwards. So what's going on there? Oh, and by the way, I hope you know that if you were actually standing out on the tarmac watching the airplane, you wouldn't see this phenomena. The reason you're seeing this phenomena is that this was recorded on either video or film that was taking a picture every so often. And that's what's displayed here. Imagine we have this wheel that's turning this amount each time. So if you track the dot, you can see that the thing is turning almost 90 degrees at every rotation. But if that dot wasn't there, you would actually see this thing going backwards just a little bit, because of the fact that you couldn't tell which one of those cross patterns was which, and so you would see it rotating backwards, okay? And that's aliasing in the temporal domain. We'll talk about that in a minute. In the spatial domain, and essentially the thing is moving too fast for how often you're sampling a time for you to actually be able to tell what's going on. The high frequency and the low frequency can't be distinguished. To show you a simple example in an artificial image, we'll see some natural ones later. Here we have a rendering, and as this checkerboard gets further away from you in the distance, right, it's supposed to start getting thinner and thinner and closer, and you'll notice that somewhere right around here, it starts to break up. It's not looking like a checkerboard look. In fact, look at this nonsense, right? It's like low frequency all over again. What's going on? Well, we can look at that in MATLAB, all right? Suppose we have this input signal. Okay, this is like that chirp that I was showing you before. Well, we can plot this as an image in MATLAB, and that would look like this, okay? So here I'm just doing x from 0 to 5 by 0.05, and I did this image of sine of 2 to the x times x, all right? And what you're seeing is, so it starts off a slow frequency, and then it's getting higher and higher, and eventually you start to see stuff that looks like that. So what's going on there? Well, that's aliasing. There are not enough pixels in the plot for you to be able to see what's going on. And that's illustrated down here where we have a small number of samples, a not dense enough sampling in order to recover those frequencies. So the question is, how can we prevent aliasing from happening? One is we can get more samples. Okay, we can join the megapixel craze in the current video technology. My birthday's coming up this month, and I treated myself to a new camera. And the camera has 36 megapixels in an image, all right, so that I can pull out really fine detail in a portrait. But in general, the sort of the megapixel thing doesn't go on forever. You know, stuff always can wiggle faster and faster as things get further away, for example. So what do you want to do? Well, what you want to do is you want to make sure your signals are less wiggly. That is, they don't have all that high frequency component. You want to get rid of some of that information. So the idea is we're going to get rid of some of the high frequency information, but that's going to be better than aliasing, right? The idea is we don't want to see that weird checkerboard effect, right? So we're going to remove some of the high frequency, but the idea is that the thing will be well behaved. So let's talk about that real quickly in our audio example. What we're going to do is we're going to introduce low-pass filters. And what the low-pass filter is going to do is we're going to put that right here, so where the analog voltage is coming out of the microphone, so that the signal that goes into the A to D converter doesn't have frequencies higher than a certain amount. We'll say, okay, great. So that says that we can reduce the number of samples we need to take, or limit the number of samples we need to take. And then when we do the reconstruction, we'll know that anything that was reconstructed that was of a higher frequency than we let in should be thrown away. So we use the low-pass filter again for the output to the speaker. So that's the hand-wavy version about aliasing. Let's be big boys and girls. Let's do this in the frequency domain. A little bit of math. The first thing we need to do is define a comb function, which is the same thing as an impulse train. So a comb function is written this. I'm not sure we've defined what this Kronecker delta function is. Basically, it's a function that's a pulse of 1 when its argument is 0 and it's 0 otherwise. And what this would mean here is as k goes from minus infinity to infinity, this thing would count up by m's. So x, every m would be a 1. So if this is 2, then this would be a separation by 2's of this impulse train. Okay? So if m gets bigger, my pulses get further and further apart. Okay, that's an impulse train. As I said before, the Fourier transform of an impulse train is another impulse train. But also, as I said before, as the spacing gets larger in space, it gets narrower in frequency. Remember, that was the scaling property of the Fourier transform. So the less often we sample in space, the higher the samples in frequency. Okay? So that's in 1D. We can also do impulses in 2D, and that's called a bed of nails, because instead of just having a train of pulses that land on the integers or some multiple of integers in 1D, it's actually lying on all the discrete coordinates in 2D, which if you're in a macabre sort of mood, you can think of as a bed of nails. So that's written here, comb of mn, because we have a separation both in the x direction and in the y direction. And also, in the same way that the Fourier transform of an impulse train is an impulse train, the Fourier transform of a bed of nails is another bed of nails. And again, as the nails get further apart, the Fourier ones get closer together. And you can think of it from the same reason. If I spread the nails out infinitely far away and I get just a single pulse in the middle of the bed, I would not recommend lying down on that single nail. That would hurt. But if you think of it as an image, it's a single impulse. It would recover. If you convolve that with your image, you'll get back the entire image. So you have to cover all the full plane in the Fourier space. Okay, and so you have to shove all those Fourier nails back together to make a flat board that you could lie on. For the discussion about aliasing, though, I'm just going to talk about this in 1D because it's a lot easier to draw the pictures and to make it clear. So hang on. What we're going to do is we're going to now talk about aliasing in the Fourier space, and we're going to talk about sampling a signal. And we'll first talk about sampling a low-frequency signal and then a high-frequency signal. Here we have a function. Here we have some nice function f, and it's a nice smooth function, let's say. All right? And it has some Fourier spectrum like this, f of u, and you'll notice that it's kind of limited, right? It doesn't have very high frequency components, like no high frequency components, very, very low. And here's our comb function pulse train, okay? And as we said before, the Fourier transform of that pulse train is another pulse train. And if the separation of the pulse train in space is m, then in frequency it's 1 over m. Now comes the point that's not so obvious. Suppose I want to take samples of a continuous function, right? I want to take a sample here and a sample here and a sample here and a sample here and a sample here. And I wanted to do it with a spacing of m. How would I do that? I actually have what I need here. I just multiply this times this and I get this. All right? That is, here is just the set of samples multiplied by f. Okay? So sampling is just multiplying your continuous signal by this discrete comb. This is why we had to introduce the notion of multiplying functions and the notion of a comb. Sampling is the multiplication of your signal by a comb. Now, when I multiply in space, what do I do in frequency? I convolve. Remember, convolution in space is multiply in frequency, and multiply in space is convolution in frequency. So what I'm going to do is I'm going to convolve the Fourier transform of f with the Fourier transform of the comb. I'm just showing the power here, and I get that. Okay, so this is the convolution, and you'll see if I just take this function and I slide it along, I'll reconstruct it here, reconstruct it here, reconstruct it there, and that's what this is showing you. Okay, so that's the Fourier transform of the multiplication of the comb times the function. Just copying that bottom row. If this function is limited, in fact, I can show it down here like this, all right, then if I could pull out that part of the signal, the part of the signal that's frequency is just within some range, then I would be able to get back what I wanted, right? I would be able to get back the original spectrum, which would give me back the original function. So this is no problem if this outer edge is small enough. That is, that the maximum frequency of my signal is low enough for the comb filter that I used. Exactly what is that small enough? Well, here it's written like this, okay? If my comb filter is spacing m, so then the comb of my Fourier of the Fourier of the comb is 1 over m. Half this distance here is 1 over 2m, okay? If the maximum frequency of that function, let's say is w, for bandwidth, is w, if that's less than 1 over 2m, then I can reconstruct that original signal by looking at just this part. That is, nothing has contaminated that inner part. So if there's no overlap, if w is less than 1 over 2m, the original signal can be recovered from its samples by low-pass filtering, which we'll talk about in a minute. So those of you that know something about Nyquist sampling, so you know that if I want to recover, say, something up to 20 kilohertz, right? 20 kilohertz about the extent of human hearing, I would need to sample at least 40 kilohertz. By the way, CDs, like we were talking about, sample at 44 kilohertz. Why? So that we can recover everything up to 22 kilohertz, which is the extent of human hearing. So as long as my frequencies are low enough, I'm okay. But what if they're not low enough? What happens? Well, now, let's suppose I have a higher frequency thing. So this is some random function, and it has some high frequency. So here's its f of u, and you see its w goes out a little bit further. If now I multiply that by the same comb of m, I'm going to convolve this thing with that 1 over m comb that I had before, and I'm going to get this part here. Now remember, these things actually sum. I'm drawing each individual component, but in reality, this thing would sum and come back up here, right? So these things would sum and come back up there. And this area right here is where this essentially, this energy has folded back on itself. It's overlapped, and then they're going to add, okay? That high frequency that was really this little edge thing here, okay, or you think of it there, is pretending it's low frequency. That's the aliasing. And once you've aliased the signal, once you've done this operation, you cannot undo it. The high frequencies have pretended that they're low frequencies, and you can't separate them out from real low frequencies. You have to remove the high frequencies before you do the sampling in order to remove the aliasing. So how might you do that? Okay? Well, how do you remove high frequencies? Well, we know how to do that. We convolve with H, maybe it's another Gaussian. What does that do? That reduces the high frequencies. So the frequency spectrum of the convolution of F and H has much less high frequency. So that H is what's referred to as an anti-aliasing filter, and it has the net effect of trimming the high frequencies of the original signal. So that then when I do the multiplication by the comb, which is shown here, right, I'm now convolving that with a comb filter in the frequency domain, but I don't get that overlap, right? So no aliasing goes on, all right? And then to recover the signal, whatever I get after I reconstruct from that using the new sampled convolved function, I can throw away any high frequencies because those are not real. That is, so just the way we did with the CD, right? We low pass filtered the microphone, did a to D conversion to get some digital samples. We did a D to A conversion to get an analog, and we knew that any high frequency that showed up, that's not real. Okay, we could low pass that away and recover the original signal. So that's summarized here in terms of aliasing. When I don't have an anti-aliasing filter, I get these overlap regions that cause me to get aliasings that I cannot remove once I've done it. But with an anti-aliasing filter, I don't get that overlap. So that's the mathematics behind aliasing. We can see this going on in images. So here's a nicer picture showing you aliasing in images. So you can see what's happening is that this is a radial sine wave. And you can see as you get closer and closer, the pixels are supposed to be wiggling faster and faster, and eventually I run out of pixels. Okay, I don't have enough samples to get how quickly the thing varies. And so that's an example of aliasing here. So what is its impact on you? Well, its impact on you is you have to be a little careful how you treat your images. For example, and this comes from Steve, all right? Suppose I've got this image, a beautiful Van Gogh picture, and suppose it's too big to fit on a screen. I want a smaller version of it. How can we reduce it? I don't know, make it half the size or a quarter of its size to do that. Well, one obvious way would be to throw away every other column and every other row, right? Just throw those away. And that's called image subsampling. Now, by the way, here it says by half. What it means is I throw away half the columns and half the rows, which of course is actually a quarter size smaller, right? But half meaning half the rows, half the columns. If I did that again, I would now have 1/4 the total rows, 1/4 the total columns, 1/16 the size. I could do it again, 1/8. In fact, you might start to notice that this is already looking a little ugly. And in fact, to make it clear exactly how ugly it is, let me blow up the half, the quarter, and the eighth by zooming in on both of them, just blowing up the pixels. And you'll notice this is atrocious, okay? The 1/2 one doesn't look too bad, but remember here, we've only taken 1 out of every 8 columns and 1 out of every 8 rows, and then we blew the thing back up. And you can see that this does not look like a blurry version of the original, okay? And the reason is we have aliasing. We have sampled too infrequently for the amount of variation that there is. Essentially, things wiggle in here more often than 1 out of every 8. And so if I just take 1/8, right, I'm not capturing all the wiggles. So what's the right thing to do? Well, we need to do that anti-aliasing. We just learned that. So a simple one is to do Gaussian, okay? So what we'll do is we'll filter, right? So we'll take the Gaussian and then take every other row, all right? And then if you want to be not so clever about this, you could do a Gaussian of that and take every other row of that to get the 1/4. And you could do the Gaussian again and do that. Or what you could do is you do a much bigger Gaussian to begin with and take 1 out of every 8. You can convince yourself that mathematically these are going to be equivalent. When I do that and I blow up the Gaussian 1/8, you'll see that this actually looks pretty much like a blurry version of that, right? Compare this to what we did with the subsampling, right? So here's sort of our original. Here is the Gaussian 1/8 4x zoom, and here is the subsample 4x zoom. And you can see that the Gaussian does a much better job in doing the reduction, and that's because it's been anti-aliased. So if you're doing computer vision and you decide, you know what, I've got this huge 1920 by 1080 image coming in, but I'm just trying to recognize faces, right? And my faces are going to be, 100 pixels big, let's say. And you say, you know what I can do is, it's going to be expensive to do that face recognition. We're going to talk about face recognition towards the end of the class. It's expensive to do that over the entire image when it's so big. Let me make the image, 1/8 its size this way, 1/8 its size that way. And I'll make my faces smaller and look for them that way. You know what? That will work pretty well if you do this, if you do anti-aliasing. If you just pull out the arbitrary pixels, right, you're going to make a mess of the whole thing. You'll get aliasing, and then the faces won't look right. So that's why doing this kind of stuff matters even in computer vision. That almost ends our lesson on frequency. There's just one more thing I wanted to talk to you about today because it's so prevalent in the processing that you're going to be doing. Some psychophysicists, Campbell and Robson, studied a long time ago the contrast sensitivity of the human vision system, not just the eye. Now, what you're looking at here is a curve where frequency goes up to the right and contrast goes up down. And probably, if you're like me, hopefully you're not like me. One of me is way more than enough, as my children will tell you. But anyway, if you're like most humans, you probably can see this stuff really well, but not so much up there. And somewhere around there, that curve is where the fall off is. That essentially, lower contrast up here, you can't really see the variation. Same thing with this high contrast. Okay, your eye is sensitive in different ways. So what this means is that some frequencies matter more in terms of the importance to you in an image. Okay? In particular, if I were to leave out a bunch of that frequencies, so that is, if there was low contrast at the high frequency, you wouldn't even know. So you can use that to do image compression. You probably have heard of JPEG. Probably have JPEG images all around you. Okay? JPEG uses something called discrete cosine transform or variations thereof. Basically, a way of thinking about that is they take a little 8x8 region of the image. So you carve the whole region up into little 8x8 segments. And then it takes as a basis set these sinusoids and cosinusoids, right? So here we have the ones that are vertical, here we have ones that are coming down, and here we have the product of them. And you can see the lower frequencies are in the top left-hand corner, and the higher frequencies are in the bottom right-hand corner. So what you can do is you can say, how much of each of these do I need to make the picture? And you can actually order them, right? You can sort of go through them and order them this way, with the idea being that the top left-hand corner might be, in fact, go back here. You see how this is a constant? Okay? So that's just the average of the picture. So the top left-hand corner, what's sometimes called B00, that's just the DC component, the average. And then as you get further and further, you're getting the higher and higher frequencies. So the top left-hand corner represent the lower frequencies. The bottom right-hand corner represents the higher frequencies. Now, what we said before is we don't have to represent the higher frequencies that well, right? Just sort of the high contrasty components of it. So one way of doing that is saying, what if we encode these coefficients better, more bits, than these coefficients? And that gives you what's called a quantization table. And DCT, discrete cosine transform, does the compression by, so What this 3 means is we keep the coefficient, say, to the nearest 3 values. So if you're thinking of this in bits, you can shift it over by 2. The idea is that you round this to the nearest 3, whereas this is rounded to the nearest 31, okay? So in other words, you're doing more representation of the top left-hand corner than you are of the bottom right-hand corner. Okay? And so what that means is you lose information, but you're mostly losing the information down here. Okay? And the same way, by the way, that you do the inverse Fourier transform, given the spectrum, you can reconstruct the signal. The same is true of the DCT. IDCT, inverse DCT, given those coefficients, I can reconstruct the image. But now, instead of maintaining all those coefficients exactly, I'm only going to keep more information about the low frequency coefficients than I am about the high frequency coefficients. And that works really well for the human vision system. And so if you take a look at your average JPEG image, and here's an example stolen from the web somewhere, okay, so they used 89,000 bytes of information to represent this picture using just the raw intensities, and 12,000 bytes here, so this is a ratio of what, 7 to 1, using DCT coefficients, the JPEG standard, all right? The reason it works, to sum this all up, is that images vary over frequency. That's our basis set. The human vision system is sensitive to different frequencies at different amounts. So by doing similar to a Fourier transform, where you take that integral or that sum, that dot product with the wiggling sinusoids, DCT is a variant of that. We can figure out the coefficients for each of the frequencies. Then we can threshold, essentially, or reduce the level of representation of the high frequency in order to save a bunch of bits in describing the image. All right, so that ends totally our lessons on frequency. I'll bet you're glad that's over. I know I am. As I said when we started this, if you were doing image processing as an electrical engineer, you would be doing a ton of work analyzing images in terms of their frequency content, and you'd be thinking about image processing operations in terms of their frequency behavior. We, however, will only do this a little bit because as computer scientists, we tend to think of images more as data structures than as signals, but we're still going to have to worry about things like frequency content when we try to do things like optical flow, where it's necessary that the image not vary very much over some distance of approximation that I make. So you'll actually have to do a filtering that sort of removes that high frequency. So hopefully you now have enough understanding of Fourier analysis and frequencies to be dangerous, and we'll go ahead and practice being dangerous in the lectures to come.